I'm really looking forward to this morning's sessions. We're really going to delve deeper into cancer therapeutics this morning in terms of doing that. And in the first presentation, we'll be delving deeper into the aspects of some of the aspects of immunotherapy that are really the cutting edge in terms of doing that. We're very fortunate that Dr. Mike Curran from the Department of Immunology at MD Anderson is going to be joining us. Mike is an expert in checkpoint therapies. He does a lot of work in that area, and particularly the issue of understanding hot versus cold tumors that are immunoreactive and those that are not. And Dr. Yubin Zhou will be talking more about the aspects of cellular-based therapies, CAR T-cell therapies, and some of the cutting-edge technologies that are coming to bear in terms of engineering cells to achieve what you want in terms of therapeutics. We're going to have follow-on presentations after to that and some other areas, a presentation on radiation therapy, and particularly how drugs are used in combination with radiation therapy to improve responses. We don't very often hear very much about how radiation works and what is happening in that field. And so Dr. Farooqi will be talking about that. And Dr. Rob Chapkin is going to give us a presentation on chemoprevention. So all of these topics are designed to basically explore the overall areas of therapeutics, not only as freestanding areas, but where combinations and integration with other forms of therapy are important. So without further ado, I'm going to turn it over to Mike and Yubin to start the discussion of, continue the discussion of immunotherapy. So Mike, you're there, I see, and Yubin. Mike's going to lead off.
Hey, everybody. So thanks for the great introduction, and thanks for the invitation to present here. I was listening to the comments, so I'm gonna keep my immunology grounded. So maybe we can all we'll all have a good immunology base for why immunotherapy has been so exciting. So that's where we're starting. How does your immune system work? Just so we're all on the same page, and it's pretty simple conceptually. Your immune system knows what makes up healthy you, and it gets rid of things that don't fit that paradigm. And so, for example, flu, although, I made this slide when it was vogue to use flu. I probably should switch to COVID. But let's see, flu has about 8 genes, only 8 small genes, yet your immune system regularly recognizes this as a foreign pathogen that needs to be eliminated. You make antibodies that neutralize the flu that's circulating around, and then you generate T cells that will recognize infected cells that have been compromised and kill them off before they can replicate the virus. Now, of course, for cancer immunotherapy, it's these T cells that we're interested in because they're the ones that can kill adulterated cells of your body. And so now switching over to cancer, why is there cancer, right? If your immune system knows everything that's healthy self, how can you actually have cancer slip through that dragnet? So tumors, have dozens to thousands of genetic changes, so far more than that flu virus we were talking about. So why doesn't the immune system always eliminate it? How can cancer even exist? And it's not a lack of potential for the immune system to recognize and eliminate cancer, but that cancer actually taps into your normal sort of reserve of genes to locally cripple your immune system and also sort of conceal itself from your immune system. And if you're wondering what these genes are, think about it. If you get an infection in your eye, you don't go blind when your immune system's going in there to eliminate that infection. So they're genes that mediate limited access or immune privilege to the eye. If you're carrying a child that's half genetically not identical to you, it's very good for us as a species that your immune system is locked out of those areas so it cannot recognize and attack that. All those same genes that mediate fetal-maternal protection are exactly the ones that tumors co-opt to protect themselves locally. So, to exist, otherwise they would be eliminated. Tumors must evolve mechanisms to locally disable and or evade the immune system. So what immunotherapy is the science of basically unmasking cancer to the immune system. It's to restore the capacity of the immune system to recognize and reject cancer. So these days, immunotherapy has become, a true pillar of oncology and has taken on many forms. T-cell checkpoint blockade, cytokines, T-cell adaptive transfer, which is what Dr. Zhou will tell you about, cancer vaccines, which has been around a long time, sort of modulating the interplay between tumor and immune metabolism, as well as, sort of more drugged antibodies. Obviously, in 25 minutes, we're not going to go through all of these. I'm going to focus on T-cell checkpoint modulation, which, T-cell checkpoints are the switches on T-cells that can be engaged by tumors to silence them before they can mediate rejection. Why are we focused on this therapeutically? Well, this has really been, the success story of immunotherapy, Jim Allison's Nobel Prize, and of course, curing former presidents in their 90s of metastatic lung cancer. This is where the attention has been drawn, right? And these are where the FDA approved immunotherapies largely stem from. So how do these checkpoint antibodies that are FDA approved, anti-CTLA-4, approved as Yervoy, anti-PD-1, Keytruda, Opdivo, there are actually 2 others now. How do they work, right? And so, tumors, again, have antigens. Antigens are, mutation-derived proteins, things that have been altered in the course of the tumor evolving into a cancer from a normal cell. These are recognized as foreign when they're picked up by an activated dendritic cell that can then show them to T cells. They'll find the naive T cells that recognize these antigens from the tumor, expand them, and now you've got an army of tumor-specific T cells. Everything's going great. They're going to go and eliminate this cancer. And in fact, the reason, most of the time we don't get cancer is because most of the time this works. But what goes wrong when it doesn't work? So when you activate T cells, they immediately start expressing these checkpoint molecules, CTLA-4, PD-1 being the most prominent. Why do they do that? Why would they express these switches that can be engaged to turn them off? Well, think about that flu infection. If you've got, billions of T cells that are going to rush into your lungs to eliminate flu-infected cells, when the flu-infected cells are gone, you don't want millions or billions of killer T cells looking around, to kill something with no appropriate target. This is how bad autoimmune complications evolve. So basically, these function as an expiration date. Anytime you activate a T cell, it activates CTLA-4, PD-1. They build up on the surface. Next time they see their ligands or triggers, PDL1, PDL2 for PD-1, or B7-1, B7-2 for CTLA-4, it turns off that response. So basically, you're setting a, let's say, 3-day expiration date on any T cells you activate. This prevents autoimmunity. However, tumors cheat, because that's what they do. They surround themselves with reprogrammed self-stroma that's enriched for very high levels of these ligands, PDL1 and PDL2. They themselves will express these ligands. So now your T cells get into the cancer, they think they're going to eliminate it, but they just get switched off by engagement of PD-1 and CTLA-4. How do we prevent this? So the drugs are actually antibodies. So they're antibodies that block the PD-1 receptor on T cells or block the CTLA-4 receptor on T cells. And with those receptors blocked, those T cells now can expand, kill tumor cells, and eliminate the cancer rather than being switched off. While this seems ostensibly simple, it is remarkably effective in settings such as melanoma, where we can have patients come in, tumors in the lung, tumors in the liver, hundreds of subcutaneous nodules. 12 weeks after combination blockade of CTLA-4 and PD-1, they're cured and durably. Where this works, I think it's a good lesson for us not to underestimate the capacity of your immune system to eliminate even bulky metastatic cancers. However, obviously, there's still cancer. So we haven't succeeded across the board. Why is that? Well, things that seem, sort of overly simplified in this cartoon are actually real problems. How do you get these T cells into the core of the tumor to mediate rejection? How can you make sure that, they actually survive in this environment? And as I'll mention, they're exposed to other influences that can also silence them. So where did this all start? So this started with Jim Allison's work. He was really the first to demonstrate that just blocking one of these off switches, CTLA-4, tumors would grow and then they would be rejected and disappear. And at the time, this was totally revolutionary. No one had any idea these kind of adaptations to silence the immune system around cancers were nearly this important. And on top of that, it established something else. So you know, where we sit here today in 2021, this seems obvious, but in 1996 to 2000, this was, you know, totally new and remarkable to people, which is every prior paradigm of oncology, you know, whether it was radiation or chemotherapy or targeted therapy, had the same, you know, the same pattern. You would give the drug, the tumor would respond, and then it would relapse and come back and be resistant to the therapy, right? Here, this is a new paradigm, one we knew from sort of vaccinology, which is that you induce immune memory that and the immune system eliminates the cancer. But now if you re-challenge these mice with the same cancer, it doesn't come back. And the critical point there is that when you have immune memory, you have sentinel protection against the recurrence of that cancer that can be lifelong. The other side is, you know, CD28 is a co-stimulatory molecule. It's the essential second signal T cells need to become fully active. And what this showed is if you block that T cell activation signal, actually the tumors grow faster. So often overlooked is the fact that, you know, even when your immune system fails to control a cancer, it successfully escapes from immune control, your immune system's still slowing it down. It's still, you know, it's still trying to mount a response, even if unsuccessful, that helps you in the end. So, you know, unfortunately, and we could talk about this in terms of inefficiencies of drug development, it took quite a while for this to get all the way through patients to approval. And this was the final study. The big difference here, you know, before this for melanoma, you know, 2-year survival was really terrible, maybe 10%, maybe 15%. And it basically over time, you know, all of these lines with chemotherapy would go to zero, right? No one really lived long term. The big difference here was that, you know, there was this 20 or 30% of patients where the curve flattened out and, you know, they were going to go on and die of something that wasn't melanoma. This was a complete change from all of the prior paradigms. So how do these work, right? And we can focus on CTLA-4. You know, there's a couple different kinds of T cells. So there's the T cells that we call effectors, that are the ones that are going to go in and attack the cancer. They're going to make inflammatory cytokines if they're CD4s. They're going to actually go in and kill the tumor if they're CD8s. You know, we know that sort of de-repressing those, blocking those off switches is really important for those. But the other kind are suppressive regulatory T cells that help the tumor, right? These are Tregs. They actually shut down normal T cell responses. In your normal body, these help protect your organs from autoimmunity. Tumors enrich them, they build them up, and they use them as a further shield to shut down your effector responses. Now, one thing about these Tregs that's different from your effector cells is that they express a ton of CTLA-4 on the surface all the time. In your effector cells, you know, when they get activated, they start expressing CTLA-4, but it's mostly kept inside the cell until that cell forms a synapse or binds to another cell, either to kill it or to become activated. And so one thing we knew about these CTLA-4 antibodies is they're going to bind up the CTLA-4 specifically on the Tregs because the Tregs have a ton of it. So what was shown is that really the critical thing is if you make a CTLA-4 antibody that just blocks but doesn't actually deplete Tregs, it has a very modest therapeutic benefit in mice. But if you make one that really efficiently, this is a very efficient depleting isotype of antibody. So basically it brings in, the antibody binds to these cells that are CTLA-4 positive. It's going to bring in NK cells to blow them up. It's going to bring in macrophages to eat them, all of those things. That just wiped out the tumors. So we know that Treg depletion is critical. I will say there was another study that showed that really both contribute in most settings though, where you got the most efficient rejection of tumors where both Treg depletion was occurring from your CTLA-4 antibody and effector sort of de-repression were both happening. Now, the reason it's worth mentioning this, I don't want to get too far into the weeds of immunology, is the drug that we have in the clinic right now, ipilimumab, so the one that blocks CTLA-4, really the first approved immunotherapy of this current generation, doesn't deplete Tregs. It doesn't do this. It's only a blocker. So, you know, we're actually underperforming relative to the potential that we've seen in mice. I mentioned that. I'm not going to go into slides or anything because we don't have time, but there are now CTLA-4 antibodies in trials in patients that have this property. And there have been some really remarkable complete responses to monotherapy in tumor indications that we couldn't treat at all with just immune checkpoint blockade, like microsatellite stable colorectal cancer. There have been complete cures of patients in the trials with the newer antibodies that can sort of, mimic this effect, right? And so, so there's real hope here that actually, even where we are, we're going to get better once we can, mice got a good deal. You give me a rodent, I can take care of their cancer, but humans, we're still getting there. Now, despite the success of CTLA-4, the real success of immunotherapy in patients has been PD-1 blocking antibodies, right? So this checkpoint is really important in human cancer. And also we can block PD-1 without the same amount of side effects, autoimmune potentiated side effects that we can get with CTLA-4. And I'll talk about that a little more, but remember what I said is the normal function of these is they put an expiration date on your T cells, so they all drop off and you don't get autoimmune reactivity. Well, when you block them, the kind of side effects you get look like sort of organ-specific outbreaks of autoimmunity. Now, to give you an idea, the PD-1 antibodies are actually approved across 30 different cancer indications right now. So these are used more widely really than any cancer drug. And in some indications, I'll give you a good example, Hodgkin's lymphoma, everybody responds. There's not much clinical need in Hodgkin's, partially because of this, but everybody responds, and 20 or 30% of these patients are cured. Now, on the other hand, you look at ovarian, where only about 10% of patients respond, and very few of these are curative responses. And so, what we see is that depending on the microenvironment of the tumor and how much it relies on these checkpoints to shut your response down, they can be wildly successful or just marginally beneficial, or in things that are not shown here, not useful at all. And so, what we've learned over time is that T cells really, there are a number of these receptors other than just sort of, CTLA-4 and PD-1 that can repress them. And there's, on the other side, a whole range of co-stimulatory receptors that can help activate them. Now, what we've also learned that we're not going to talk about in this is that antigen-presenting cells or myeloid cells also have both co-stimulatory and co-inhibitory receptors. So the way that we drug this therapeutically, we make antibodies to block these negative signals or these off switches on T cells. And we make agonist antibodies to activate the co-stimulatory ones that make them expand better, make them better killers, et cetera. And what I'll talk about is, the FDA approved drugs are all here: PD-L1, CTLA-4, PD-1. So I thought I'd talk a little bit, this was a long time ago when I was a fellow with Jim Allison, how we decided that CTLA-4 and PD-1 should be blocked together. Because what the field is doing right now is still trying to find the best combinations of these that are synergistic. And this is what guided our development of this combination of CTLA-4 and PD-1 blockade. Quite simply, we realized that when you blocked PD-1, we saw CTLA-4 building up more and more and more on the T cells in the tumor. Likewise, if you block CTLA-4, we saw more and more PD-1 building up on the T cells in the tumor. So these two actually, could complement each other. Loss of one just led to shutdown of the T cell through the other. And so we felt that by blocking them together, also knowing that they had very different phenotypes in knockout mice, we could get a synergistic effect. And that's really what we saw in this model of melanoma. You block any of these, you can cure 10, 20% of animals, block the two together, 50% of animals get cured, and then sort of shut down this whole PD-1 pathway. And now, 3/4 of the animals are getting cured. So you go from a tumor that's completely intransigent to one that's largely manageable. And this is certainly where we've tried to get to with combinations in the clinic. And just in case you're wondering, by blocking PD-L1 and PD-1, I won't go into the details, but there are actually a number of interactions in the circuit, including one that involves PD-L1 binding to B7-1 that is not blocked by the PD-1 antibodies alone. This is what you're getting when you add PD-L1. So thinking about potential synergy between, blocking these off switches on T cells, how do we know which ones are redundant, which ones, other than just sort of this observational, therapeutic response that I showed you? Well, another way, so this was done by Bob Schreiber's lab in the mouse. Matt Yubin, who's a faculty at MD Anderson now, actually was the first author on this. And really, genetically, you can see synergy here, right? So PD-1, improves T cell metabolism when you block it. CTLA-4 really improves cell cycle and development of T cell memory. But together, you've got this 400 genes in mice that get turned on that are really involved in making a really good anti-tumor responses, that the kind of things you'd want. better effector function, better cytokines, better proliferation, and they're only turned on when both of these switches are shut off. Largely, this is driven by the fact that either one of them can activate SHIP phosphatases to shut down signaling downstream of the T cell receptor and CD28. Very often, we don't see great concordance between mouse and human. When you do see great concordance between mouse and human, you usually know you're onto pathways that are important and very well conserved. You can see it's almost the same. Here there's about 390 genes that get turned on synergistically, about the same, but about 400 in humans in Rita Pernodas's work. Very, very conserved de-repression of T cells you see with combination blockade between mice and humans. Now, when we looked at the cellular level, again, one thing we always look for in melanoma was, what's the ratio of these CD8 positive effector T cells we need to kill and reduce this tumor versus regulatory T cells that are trying to block this response, right? And with CTLA-4 blockade alone, we could see that these ratios got better. Instead of 1-to-1, we had about 10 CD8s for every suppressive Treg. But you see, when you shut down this whole pathway, all of a sudden you're in kind of unprecedented territory here, right? 40, 60, 80, 100 CD8s for every Treg means that tumor is getting eliminated, right? And so this was very strong. To give you the historical bent on it, this was very strong evidence saying we should do this in patients, right? We should block both CTLA-4 and PD-1. However, the other side of that argument was, well, it might be therapeutically effective, but can people tolerate that? And so now I want to give a little more detail when we talk about the immune-related adverse events. So the downside to de-repressing, taking these breaks off your immune system, what we see are a whole range of itises, right? And the ones that can really hurt you, pneumonitis, very severe colitis, these are things that can be life-threatening, right? And so the fear was that, especially with some overlap in terms of colitis, thyroiditis, hepatitis, that by putting these together, no one might be able to actually tolerate the therapy. The good news was when we did this, although the frequency of the side effects increased, their severity did not. And so, these patients are still manageable, steroids, et cetera, the way that we manage these immune-related adverse events. But for once, we do a lot of things in mice that don't pan out when we get into humans, right? We're really good at curing mice of cancer. It doesn't always work when we go to patients. This was one of the very gratifying times when, look, as I mentioned, melanoma, as recently as 2010, the 2-year survival was about 18%. Here now it's 80%. You've got a very substantial percentage of durably cured patients of metastatic melanoma. These days, the objective response rate is actually closer to 60%. This was the phase 1 trial. And this combination is now used in lung, it's used in renal cell, it's used in a number of other indications. And the major downside is the side effects, though. And so the goal in the field is find ways certainly to improve efficacy while at the same time improving tolerability so more patients can get this and benefit. All right, so how do we know who the right patients are? Like what patients should we treat with immunotherapy? So when it comes to blocking PD-1, kind of an obvious biomarker, but one that gets used a lot is, do patients have PD-L1, this ligand, this trigger that's going to hit PD-1 and turn off the T cells? Well, where do we find PD-L1? Well, the reason it's a good trigger, one of them, is that certainly there are tumor intrinsic pathways that turn on PD-L1. Things like EGFR, things like hypoxia will turn on PD-L1. But we see a lot of PD-L1 turned on in tumors, tumor-associated myeloid cells, also T cells in the tumor microenvironment, when they see interferons. Both interferon gamma as well as type 1 interferons are real strong inducers of PD-L1 and its sort of sister ligand PD-L2. So we know if there's PD-L1, there's probably some immune infiltration of that cancer, which is already a good sign that maybe there's some T cells there we can de-repress and activate to get rid of this tumor. And so if we see these patients with PD-L1, we know they're more likely to respond to PD-1 treatment. And we see that with the PD-1 antibodies, right? This is melanoma again. And you see if patients have more than 1% immunohistochemical staining of PD-L1 in their tumor, they do just as well when we give them PD-1 blockade, which is in the blue, as they do when we give them a combination of PD-1 and CTLA-4, which is in the orange. So those patients, if you come into the clinic and you have PD-L1 that's 5 or 10 or 20% of your tumor, you're going to get PD-1 blockade and you're probably going to do pretty well. The problem is a lot of patients come in and they don't have very much PD-L1 in the tumor. And those patients, there's still some, you can mobilize a T cell response from outside. It will start to infiltrate. Things will still benefit, but a minority of patients will then benefit from PD-1 blockade, right? If you have low PD-L1 in the tumor, your odds of benefiting from CTLA-4 and PD-1 are about the same. They're maybe like 20%, right? But the combination of CTLA-4 and PD-1, again, because of that synergistic benefit in terms of potentiating T cell responses, is just as effective in patients with low PD-L1 as patients with high PD-L1. So if you come in and you have tumor with melanoma particularly, and you have low PD-L1, you're going to get the combination, right? And so this is how we've leveraged biomarkers. There's a real movement in the field, and this is one sort of simple example, to improve our use of biomarkers to know the right patients who are going to benefit from the right therapy without having to sort of max everyone out and cause a lot of toxicity that's unnecessary. All right, however, so that's the good news. But the reality is, with the exception of microsatellite and stable cancers of all kinds, Hodgkin's, cutaneous melanoma, actually, I should have put non-small cell lung cancer here. The majority of patients actually still fail to respond to T cell checkpoint blockade. We can actually we have approved indications to treat almost 50% of oncology patients with some form of checkpoint blockade now, but the actual objective response rate in that 50% of patients is only 15 or 20%. So the majority still don't respond. So a major challenge in the field is to understand what are the factors governing immunotherapy resistance. And this really tells you, you see this terminology a lot, right? What's a hot cancer? Hot cancers have actually that legend didn't copy very well, but they have high mutation burden. So lots of mutations that are immune visible. And then they have a lot of inflammatory gene signature, which means they have a lot of pre-existing immune infiltration. Both of those, your melanoma, your non-small cell lung, your Merkel cell carcinoma, you're going to respond super well to checkpoint blockade. Unfortunately, as I mentioned, the majority of cancers, 55% of patients who walk through the door, low mutational burden, few neoantigens for the immune system to latch onto, low pre-existing immune infiltration. These patients do very poorly when we try to give them checkpoint blockade. And this again shows you where we're still falling short, even in this 45% of patients that we do have approved indications for. The objective response rate, it's gotten a little better since this figure, but it's still around 15%. It's not great. So what are some reasons for failure? Even in melanoma, we celebrate the 60% of patients that respond. We also want to understand, what happens in those 40% of patients that don't respond. And this was a great study by Roger Lowe that showed that, some of them have, very advanced sort of EMT. That's always a bad prognostic factor for immunotherapy for reasons that we're understanding better now. Angiogenesis and hypoxia are certainly related. When there's hypoxia, your immune system actually does not function well under hypoxia. You get both intrinsic and extrinsic suppression of T cell responses. And of course, lack of interferon response. Your T cells really need interferon to induce tumors to become immune visible, to co-opt the tumor myeloid repertoire to be immune supportive. When those things aren't working, you may fall short. So there have been a number of studies, and I thought I'd just mention a couple. So this was a really pivotal study by Stephanie Spranger when she was still in Tom Gajewski's lab. But she showed, if you have beta-catenin activation, so Wnt beta-catenin pathway, one thing that happens is you can have a tumor that has, for instance, pretty good sensitivity to just CTLA-4 and PD-1. This is a spontaneous model, mimics some of the most common mutations in melanoma, BRAF activation and PTEN loss. Pretty responsive. Add beta-catenin activation, not responsive at all. Completely not responsive. So, why is that? Why would just activating the beta-catenin pathway stop your immune system from being able to recognize this cancer? What they showed is that when that happens, the tumors stop making a chemokine that attracts dendritic cells to the cancer, right? So now you have a cancer, it has mutations that can be recognized by the immune system, but you're missing that piece where those antigen presenting cells have to pick up tumor antigen and show it to your T cells for them to become active. So we call that state immune ignorance, right? you have an organism with a capacity to mount an immune response against the cancer, but it never becomes aware of the antigens in the tumor that it would need to attack. How do you fix this? Well, in this case, they fixed it by introducing FLAT3 ligand generated CDC1, so bone marrow derived dendritic cells. So basically they forced the dendritic cells back in the tumor where they had been sort of pushed out by this beta-catenin mutation. And now if you give checkpoint blockade, almost all the cancers are rejected, right? So it's important to understand these origins of sort of immune desert status or immune ignorance so that we can understand how to reverse them. But in a more general sense, this gets back to this question of, okay, this is so great for melanoma. Why doesn't it work for pancreatic? Why doesn't it work for castrate-resistant prostate? And really, there's a whole host of other immunosuppressive signals originating from the tumor stroma as well as the tumor that can be immunosuppressively dominant over just release from checkpoint blockade, right? There are more than one ways for the tumor to shut down T cells. We have a real advantage now if the tumors are relying on engagement of PD-1, engagement of CTLA-4 as their only modality to protect them from the immune response. But, the myeloid stroma of tumors make a whole range of factors, IDO, which degrades tryptophan and makes kynurenines, adenosine release, arginase release that degrades arginine, which T cells really need to sense in order to become active, TGF beta, other suppressive cytokines, IL-10, IL-35, metabolic competition. All of these are ways that can be dominant over checkpoint blockade. And this is really where the field has gone, looking at ways to rectify these additional barriers. So PD-1 and CTLA-4 blockade potentially impact T cell function, but no other modulators of T cell co-stimulation have reached clinical approval. I showed you that slide. There's a T cell with, 10 different receptors. Why hasn't blocking any of those others added additional benefit, right? This one. So those are the ones that have been FDA approved. All that keeps happening is we FDA approve more of those. I'm going to finish in a second so I don't take Dr. Zhao's time anymore. So what about co-stimulation? And I just want to talk briefly about the other side of the equation. Interestingly, now we even have drugs targeting CD28, which is a whole nother story for another time. But, this is not science. This is an opinion piece that I put together just to condense some of this for you guys. But if you need a guide, because there's so many of these and you're not quite sure how to understand which ones might be promising or not, when you think of them therapeutically, there's a couple things to think about. How much is it expressed, right? It may be super repressive, but if the expression's low, how many patients are going to benefit from blocking it? How much activity does it have, right? So LAG3 is finally showing some benefit in combination. As a monotherapy, it never showed any benefit when people blocked it with antibodies. Why is that? Even though its expression is high, it's not as sort of per molecule suppressive as things like PD-1 and CTLA-4. So you need to use it in combination with other things. What about toxicity? Like if there was a trial with a Vista antibody, it was so toxic, it didn't make it very far. Now we think we can get around this by sort of going at this different ways. But obviously, if it's too toxic, no matter what the benefit is, it's not going to be viable. All of these things have limited success in the field. And so now we have TIGIT antibodies, probably will be the next approved. Co-stimulatory antibodies, we have none that are approved, but now we have 4-1BB and CD40 that are sort of making their way that way because we have figured out ways to overcome this toxicity. So can these agonist antibodies work in patients? 4-1BB has always been the best target to go after. Why is that? It's not expressed on naive T cells. If you're making an activating antibody, you don't want to activate naive T cells. The prior CD28 experience showed that. We don't talk about that right now. You'll create cytokine release syndrome. You'll activate T cells that are not tumor specific. None of that is good. 4-1BB is specifically expressed on effectors. That's great. You can activate all your tumor specific cells, and then it's retained on memory. This is a perfect profile. Unlike things like CTLA-4 and PD-1. CTLA-4 and PD-1 amplify, they sort of make a T cell more of what it is. They'll divide more. If they're a Th1 cell, you get more Th1 cells. If they're a Th2 cell that's sort of more, allergy oriented, you'll get more of that. If they're a Th17 cell that's sort of more inflammatory, you'll get more of that. It doesn't change the nature of the programming of the cell as much as it just unleashes it and expands it and amplifies its function. That's different with co-stimulatory agonists. So 4-1BB will reprogram cells to a unique phenotype that makes them highly cytotoxic and really strong expressors of inflammatory cytokines. So even if it started out as sort of a phenotype that is not useful for anti-tumor activity, like a Th17 cell that can be tumor promoting and colorectal, or a Th2 type cell that can make tumor supportive cytokines like IL-4, the difference with things like 4-1BB is it will turn them into the kind of cell you want for anti-tumor responses. The nice thing about 4-1BB too, it mostly acts on CD8s, but can also act beneficially across myeloid cells, particularly on dendritic cells. In humans, also has benefits on CD4 T cells, not in mice. People have shown, for decades now that, blocking 4-1BB, or sorry, activating 4-1BB with this antibody, anti-4-1BB, CD137 is 4-1BB. So the agonist antibody activation of 4-1BB alone as a monotherapy can induce rejection of cancers in mice. Over that time, 4-1BB agonist antibodies alone or in combination with standard therapies or others have been used to treat just about every mouse cancer that we have. Different from things like CTLA-4 and PD-1. I mentioned we block CTLA-4, we block PD-1, we get more autoimmunity. You activate 4-1BB, you actually suppress autoimmunity. And we figured out why that was, which is that, most autoimmune disease, things like mouse MS or mouse arthritis, collagen-induced arthritis, or EAE, they're very Th17 dependent. So they depend on the cytokine IL-17 and the associated inflammatory cascade. This factor, transcription factor, iomesodermin, is induced very strongly in T cells by 4-1BB. It represses Th17 responses in T cells, basically prevents them from being able to make Th17 cytokines. You also, when you activate myeloid cells with 4-1BB, you make IL-27. That's a trans repressor of Th17. So you get the best of both worlds. You get suppression of autoimmunity and you get activation of tumor immunity. Why do we not have approved drugs here? Well, the reason is 4-1BB also causes immune infiltration of the liver. And you see with that, you get activation of transaminases, elevation, both actually ALT and AST. Now, we showed some interesting things, such as that you do get this activation of transaminases, so liver damage is what these represent with 4-1BB. If you also add CTLA-4 blockade, you ameliorate that. But if you give all three together, add PD-1, it breaks through again. And so, there may be some interesting potential in the clinic to control this by combining 4-1BB and CTLA-4, and that's actually going to happen soon. But this has been the problem. The first 4-1BB agonist antibody failed because of liver toxicity. Oh, sorry, go ahead.
So I just want to be sure that we have time also to.
Sorry, I think I have 2 more slides and I'll go super fast. You know, I appreciate it. Sorry.
Thank you.
No problem. No, it's good. So just the paradigm I wanted to introduce, because this is how people are trying to circumvent toxicity with all of these things, whether it's, CTLA-4 blocking antibodies, 4-1BB agonist antibodies, CD40 agonist antibodies. To get around this, people are constructing bispecifics, right? So all the toxicity from 4-1BB comes from, if you activate it in the liver, you get bad things that prevent you from using it in the tumor. So now people have generated bispecific antibodies where you have a high affinity tumor antigen arm that anchors the antibody, forces it into the tumor out of places that it can cause autoreactivity like the liver, and then a weaker agonist that's dependent on, this being cross-linked first. So as it circulates, you get no activation of 4-1BB. Only when it's bound in the tumor environment does 4-1BB get activated. There's a whole slew of these antibodies for both 4-1BB, CD40, and others that are now in phase 2 clinical trials. So the goal of T-cell checkpoint blockade, just to remind you, is to block the switches on T cells being engaged by the tumor to shut them down, and in so doing, restore tumor-specific immunity. I'm now going to turn it over to Dr. Zhou. Sorry for taking a little too long. Who's going to tell you about T-cell therapy. Thank you so much.
Thank you very much, Mike. And Yubin.
Yes, I'll take over. Thanks, Mike, for the great introduction. Saved me a lot of introduction time, actually. So it doesn't matter, even 10 minutes. I'll try to get it done within 20 minutes if possible.
Thank you. I'll intervene at 20 minutes either way.
Yes, I will set up a timer. So
Sure.
I won't talk over time because I don't want to occupy the discussion time. Okay, so I will take over from Mike. So Mike has been talking about the brake side. If you imagine the immunotherapy is it's like you're driving a car. So Mike has been talking about how to release a brake by using the immunocheckpoint blockers. Now I want to focus on how you're going to step on these gas pedals so you can boost in the anti-tumor immunity by using the cell-based therapy such as CAR T therapies. So this is just a joke. If you press on both the gas and the brakes pedals, you got a screenshot, but actually it's not. No. So it will be in 4 small sections. One, I will introduce you the design principles and give you some examples of the efficacy of the CAR T therapy based on the current state of the art, and also mention about some side effects we have to face during these CAR T therapies. And in the last section, I will also give you some the next generation CAR T and the most ideal CAR T therapy will look like. So I think Dr. Rooney yesterday gave you a brief introduction about CAR T therapies. I will try to make it short here. So basically, it's called a chimeric antigen receptor because the engineered receptor is made of different signaling molecules from different signaling proteins. For example, the T cell has a signal 1 and a signal 2 from the antigen presenting cells to be activated. So the signal 1 and 2 was conveyed by different modules in the T cell receptors. And we can wind all these signal 1 and the signal 2 modules into a single construct. It's called a CAR, chimeric antigen receptors. Basically, you can put a co-stimulatory molecules and also the stimulatory molecules, CD3 zeta, chains into a single construct. So to make it independent on the MHC presentation, this is how the nature immunity system works. Basically, you have to have the antigen presenting cell presented antigen to T cells to bypass that requirement. So a single chain fragment variable derived from antibody actually is used, basically fusing the light and a heavy chain of the variable region of the antibody into a single construct. So all this is made of, by using some hybrid, genetic engineering approach, and you can only, the only thing you need is to express this into T cells, and then you infuse a T cell back to the patient so they can recognize the tumor antigen and mounting the anti-tumor immunity. So here's a very simplified cartoon explain how the CAR T cell works. As I mentioned, the scFv component can engage tumor antigens. So once they encounter tumor antigens presented by the tumor cells, they can activate in a very complicated signaling cascade, will ultimately leading to the effect function of T cells. In this case, for example, the CD8 T cells will be instructed to produce proteins such as perforin and granzymes, and then they can make holes on the cell surface of the cancer cells. So that is the reason why they can engage tumor cells and kill them in a very efficient way. So here is a very, very brief history showing the development history of the CAR T therapy over the past 30 years. And as I mentioned, you can put different modules into these CAR T, into the CAR antigens and antigens. Now, just like CAR can evolve, from the very, very prototypical model back into the 19th century. So now we have very, very fancy race cars. So basically, you keep putting a lot of more modules into CAR Ts so that you can get a better efficacy with a reduced side effects. So far, there's 5 FDA approved CAR T therapies, which I will show you in the following slides. And as you can see, the cartoon here showing on the right here is showing how different generations of the CAR has been developed, so they can do more complicated things. Actually, the clinically approved CAR T is all based on second generation. Basically, it has a single chain fragment variable recognizing tumor antigens, and also have one co-stimulatory molecules, either for 1BB, as Mike mentioned, or CD28 fragments. And then this is the stimulatory molecules. Basically, it's phosphorylation modules derived from CD3 zeta. So the advantage of a CAR T, it is a live drug. Basically, these are live T cells injected into the tumor patient, patient with tumors, and also the CAR T is independent on MHC, so it does not need the antigen presenting cell to present antigens to the T cells. They can automatically recognize in tumor cells by themselves. And because this can be, the scFv component can be changed to any, tumor antigen you wish. So you can do like a multi-anti-tumor immunomodulator. It can be engineered into the CAR T cells, and also the targeting antigens can be swapped, very, very easily. But basically, you just simplify to simply to replacing the scFv components, and you can make a new CAR Ts. So here's a list of the 5 FDA-approved CAR T cell therapies. As you can see, most of them is directed, almost all of them is directed against, liquid, tumors like mostly it's like a B cell O's and also diffuse large B cell lymphomas. And the only newly addition to the tool is the anti-B cell maturation antigen, just approved a few months ago. This year, it's tried to targeting the multiple myelars in the patients, and the other 4 clinically approved CAR T therapies all engaging the CD19 positive tumors. Mostly it's B cell lymphomas. So what about the efficacy of this in the clinical settings? So these are the 2 typical the first 2 FDA approved CAR T therapies. One thing I want to bring to attention is the price is very expensive. A single therapy costing almost $0.4 to $0.5 million. So this is why in the last section I will mention there's a need to reduce the cost so it can make it more applicable to most of the patients. And here is a very simplified cartoon explain how the CAR T therapy works. Basically, you take the T cells, actually it's a peripheral blood mononuclear cells from the patient, and then you culture them, expand them, and then you using a virus like lentivirus or retrovirus to transduce the cells, so you can express in the chimeric antigen receptors in T cells, so they become CAR T cells. And then you infuse this back into the patient, and then the CAR T cell can recognize the tumors to leading to the tumor killing in the patients. So the CAR T therapy has achieved miraculous clinical efficacy in patients. For example, this is the first clinical trial done almost 11 years ago, July of 2010. So the patient actually survived for almost 10 years. Unfortunately, he was died of COVID-19 pneumonia, but it's not a died of the tumor or the cancer per se, but it's because of the COVID-19 pneumonia. And the second case is the very famous Emily Whitehead. She also actually had a foundation established to increase awareness of the CAR T therapy in the cancer patients. Basically, he received the therapy 10 years ago, and till now, at least 3 months ago, this is a blog, May 10, 2021. So she's celebrating 9 years cancer-free. So this is just 2 examples showing how the CAR T therapy might have a curative potential in certain patients. So what about in a large population of patients? So this is the summary of multi-center international clinical trial results showing the 75 patients receiving CAR T therapies. You can see upon 6 months, almost over 70% of patients, they can have event-free survivals. And the overall survival, if you judge them by half year, it's very, very, powerful. It's over 90%. Even after almost 2 years, you can see almost 50% of patients they can survive without any, major clinical symptoms. However, in almost, more than 50% of patients, they had an issue because they will develop some tumor antigen escape, because the tumor, if they relapse, they will remain CD19 negative. Basically, this is the tumor antigen being engaged by the CAR T therapy. So if they relapse, it will also impose a second question is how they can be killed by CAR T therapies, because the CD19 antigen becomes negative in those tumors. And in the last 2 slides, I will mention about a strategy to overcome this tumor antigen escape issues. So I would after you presenting the high efficacy of the CAR T therapies, I also want to mention to you about, two notable side effects associated with CAR T therapies, and present to you one case study so you have a better, sense about what the side effects looks like in patients. So the challenge facing the CAR T therapy is it has very, very, severe, side effects. And then mostly it's, falls in two categories. One is a cytokine release syndromes. Basically the T cell, once they activate in the tumor site, they can produce a lot of cytokines to activating macrophage and also a lot of other myeloid cells. And the second side effects associated with on-target off-tumor toxicity, because the existing CAR T therapy is engaging tumor-specific, antigens. It has been claimed to be tumor-specific, but in normal tissues actually also have some low expression level of those tumors, those antigens that is exactly the same as the tumor cell has. It's just a matter of how much you express in tumor cell versus, in normal cells. So as you can see here, almost, all the patients, with the response to treatment in this, clinical trial, they had a B cell aplasia in the long term. That means their B cell will also be depleted because normal B cell will also be targeted by the CAR T cells in the long run. And also they can develop in some very, very severe side effects, such as neurotoxicity and cytokine release syndromes. So this slide actually explain, this is the current understanding of the, the mechanisms underlying those side effects. As I mentioned, these are the tumor cells, antigens, recognized by CAR T cells. So the CAR T cell will be activated. It can produce a lot of cytokines. So the cytokine actually can also activating, macrophages. This can lead into a self-amplifying inflammatory activation loops in macrophages. They can produce a lot of interleukin-6 and interleukin-1. And interleukin-6 is very, very, inflammatory. It can lead into cytokine release syndromes. And IL-1 actually, they can also go into the, into the brain, so they can lead into some inflammation, in the neuro, leading to the neurotoxicities. So those are the two major, cytokines that is responsible for the, the side effects associated with cytokine storms. So in the clinical settings, two antibody actually has been developed to reduce the cytokine release syndromes. One is called tocilizumab, and it's IL-6 receptor antibody, or it's the other one is called anakinra. Basically, it's can neutralize the IL-1, so they can mitigating the neurotoxicity in the clinical settings. And here I would like to presenting a very a real case you see in the clinical settings. So this is a 34-year-old female that has a refractory diffuse large B-cell lymphoma. She actually received a lot of rigorous a very, very aggressive chemotherapy, but she actually relapsed after the chemotherapies. So then she was admitted in the hospital and receiving the CAR T therapies. So on the day one, after infusion of the CAR T cell in the patient, basically the patient, you can see the blue line here. You can see on the day one after infusion, he showed a very high fever. And if you look at this, other clinical signs, you can see the green curve here. You can see the systolic. This is a blood pressure, systolic, blood pressure drops. So he has hypotension. Basically, it drops all the way up to down to 84 millimeter the level. So it was diagnosed as a grade 1 cytokine release syndromes. So he just received some normal treatment, just just like the Tylenol, to reduce the fever, and also did IV with this human IL-6R monoclonal antibody. And you can see that, on a day 3, actually the scenario getting worse because the patient, you can see the oxygen level, which is shown the green curve, the yellow curve right here. You can see the oxygen level on the day 3 drops. So it's developing some hypoxia syndromes. So the patient was, supplied by some nasal oxygens, and in addition to the antibody therapies to reducing the IL-6, productions. And on day 5, you can see this is trying to monitoring whether or not the patient, losing the, conscious by, asking the patient to write some letters. You can see on day 5, he developed the symptoms like dysgraphia. Basically, he has a difficulty to write or recognizing letters. And also he can, the patient was diagnosed of a grade 2 confusions. So this is a typical example for neurotoxicity associated with CAR T therapies. And the patient again was, infused with this anti-IL-6 monoclonal antibody, and also basically receiving some supportive cares. And on day 9, very, very dramatic, change happened. Actually, the patient, if you look at it here, after day 5, the temperature drops and the heart rate is back to the normal, and the oxygen level back to the normal, and also the blood pressure gradually becoming normals. And I want to also mention, this is a C-reactive protein level. This is showing the immune response. You can see all this, going back to the normal levels. And after 1 month, you can see the, miraculous, clinical outcomes. This is showing the, lymphoma in the, in the abdomen. You can see, this, a tumor mass actually disappeared after 30 days of therapy. So this is leading to a complete remission of the patient within, a single month, treatment. So basically, this is a very typical case study showing the toxicities, and also, how this can achieve in a complete remission in the patients in the clinical settings. So this is the basic, toxicity management algorithms. If the patient developing some CRRs, cytokine release syndromes, they will be administered by these anti-IL-6 or anti-IL-6 monoclonal antibodies to reducing the side effects. And also, if they have some neurotoxicity, they will be, receiving some corticosteroids in some of the patients. And of course, this is the basic, supportive care for patients with a CRS. And if you have time, you can look at those, how, each steps, will be exactly in the clinical setting to deal with the, complicated, side effects.
You have about 5 minutes, Yubin.
So in the, last 5 minutes, I will just give you, some of the latest, progress, in the CAR T-cell therapy, field. Basically, how you can, develop in the smart CAR T-cells to overcome some of the patient, clinical problems associated with patients, and also how we can develop in better, therapies to go after solid tumors, which is a major challenge in the field so far, and also how we can reduce the cost associated with the CAR T therapies. So the current challenge in the CAR T-cell therapy, as I mentioned in the beginning, you will have an antigen escape, and also for solid tumors, this is the most difficult problem in the clinical setting, is how you can more efficiently making the CAR T-cells infiltrate into the tumor sites, and also how to overcome these immunosuppressive tumor environments. And also, I mentioned how we can develop in therapies to mitigate or to reduce these CAR T-cell associated toxicities. So if you look at those problems, if you try to draw a diagram by using 5 parameters, one is a control, and second is a recognition issues, and the third is trafficking issues, and the third is how to maintain the long-term, proliferation and the persistence of the CAR T-cells when you infuse in the patient. And the last one is how to overcome this, tumor suppressive, microenvironment in the tumor sites. So the black curve showing here is the current, stage of the, therapies we have. And the most ideal, of course, we hope we can achieve in some satisfactory, efficacy by showing, satisfactory outcomes in all these 5 parameters. Basically, we hope we can, developing CAR T-cells have a better or more accurate, tumor antigen, engagement, and they can be, you can precisely control them, and also you can, fight against the tumor microenvironment, and also maintain a long-term memory, so they can persist a long time in the patients, and also we can, enhance the trafficking to the tumor sites. So to address the control problems, there's some other, way, there's a lot of, strategy has been developed. One of the strategies try to using small molecules to control the signal 1 and the signal 2 in the CAR T cells. For example, you can split the, two, the co-stimulatory and a stimulatory signal in 2 constructs. And then once you add in a drug, you can restore the CAR T functions. So you can titrate the CAR T cell, activation by using the drugs. Or alternatively, we have been, showing that we could also use a light. For example, you can make a light sensitive modules in the CAR T cells. So you can use a light to titrate the anti-tumor, response. So you can use a light or chemicals to control the CAR T cell activations. So this is showing you, how you can, make this happen. The conventional CAR T, basically, they have signal 1 and 2 in a single constructs. And then once they encounter tumor antigens, they can mount an anti-tumor, immunity, so they can kill the tumor cells, basically integrating signal 1 and 2 in a single constructs. the solution to avoid a lot of cytokine production is to separate the signal one between two constructs, and you with some chemical or sunlight you can re-engage the CAR T cell activation. In this case, you can turn on and turn off CAR T. So you basically put a safety on switch in the CAR T cells, and yeah. So 2 more minutes, I guess, Peter, right? So try to address the recognition issues. There's some recent creative idea being made in the academia in the field. Basically, is try to hijacking the notch signaling pathways. Basically, it's mimicking the notch signaling pathways. Once the antigen has been recognized by the T cells, they can actually lead into the cleavage of the effector domain here. So you can make this effector domain go into from the plasma membrane into the nucleus. You can turn on gene expressions. For example, in this case, you can do logical gating in T cells. For example, when they recognize antigen A, which is shown green here, they can instruct the CAR T cells to produce another CAR, so they can recognize the antigen B. In this case, they can, only in the presence of antigen A and B, the CAR T cell will be activated. So that can, by putting a lot of more, antigen recognition modules in CAR Ts, you can increase in the specificity. And the third issue I mentioned is the tumor escape issues. For example, in over 50% of patients has relapsed after CAR T therapy, they losing the capability to recognize the CD19 antigens. In this case, you can put two antigens. For example, you can put a CD19 or CD22, and then so that even the escape one antigens, the other antigen still can be recognized. So the CAR T cell still can engage the tumor cell to kill them. And actually, in a recent paper showing that CAR T cells with the dual targeting of CD19 and 22 shown very, very promising, clinical efficacy in the refractory B cell malignancies. The fourth issue I want to mention here is how to addressing the trafficking issue. Basically, you can increase in the expression of some chemokine receptors, for example, the CCR2B in the CAR T cells. In this way, they can recognize the tumor cells, and they can be more efficiently, infiltrated into the tumor site, so they can engage tumor cell to kill them. And indeed, there's some clinical trial ongoing, and it's showing very, very promising results. It's yet to be finally approved by FDA in the next couple of 2 or 3 years. And if you're interested, you can look into this, references I will show this. And the last, question I want to mention here is to addressing the tumor microenvironment and the persistent issues. So as Michael mentioned, the immunocheckpoint, blocks, basically it's using the anti-PD-1 or anti-PD-L1 antibodies to try to relieve in the break, in the tumor, suppressive in the tumor microenvironment. So actually those, CPB, therapy actually can be coupled with CAR Ts. So you can reactivating the CAR T cells when they undergo exhaustions in the tumor microenvironment. So they can be reactivated so that CAR T cell can keep killing the T cells, tumor cells. So there are a lot of ways you can use. For example, you can combine CAR T cells with some anti-PD-1, anti-PD-L1 antibody-based therapies. You could also express in a dominant negative region of the PD-1 in the CAR T cells, so they will recognize the suppressive signals in the tumor cells, but they will blocking the transmission of the signal to the T cells. You could also use some single chain fragment to neutralize it. And ultimately, you could also do some genome editing to removing the PD-1 expression in the CAR T cells, so they will not be suppressed by the tumor cells. And there's a lot of clinical trial actually up to 6 actually has been ongoing in the clinical settings, try to combine the checkpoint blockers with the CAR T cells, and we the final clinical efficacy are yet to be clearly established. So then, I will just try to stop here with these slides. This is a very growing need for the CAR T cell therapy. You can see 3 years later you will see a market of about $10.4 billion. So there's a lot of growth potential here, and till 3 years later, we hope we can get a much more clinical approval from FDA for the CAR T cell therapies. I will stop right here.
Thank you so much, Mike and Yubin, for a really superb session. I think what we will do is for those people who have to leave to take advantage of the break for any reason, please feel free to. But let's take a few minutes to have some discussion and questions before at 10:15 we move on to the next session. So if you could release the screen, Yubin, maybe we could see if people have.
I do want to mention too that Don has set up a folder. I know Mike has already shared his slides, Yubin. I don't know if you're going to send us your slides, but for all the slides that are being shared, you'll be able to access them in a folder. And so hopefully we'll have that link shortly.
And some of you may have follow-up questions with Yubin or Mike. You can do offline afterwards. Ryan, I see you have a question there.
Yeah, I have a question for Mike. I was wondering if we can use that antibody therapy in combination with a small molecule, because I know that, for example, you were talking about adenosine that can induce an immunosuppressive effect. And I was thinking if we can use a small molecule that can target an enzyme that release adenosine or adenosine receptors.
Yeah, no, it's a good question. So a lot of the approaches to sort of block some of these adjunct suppressive mechanisms that are coming, particularly from the myeloid stroma, involve combining, exactly as you suggested, small molecule based targeted therapies with immunotherapy. And in particular, there have been some pretty promising early phase trials with adenosine receptor antagonists, which are, I mean, there are antibody variants, but generally small molecule A2A, A2B blockers in combination with PD-L1 antibodies. And those have looked really promising, even in some patients who had already failed PD-L1 antibody monotherapy. And certainly there are other small molecule sort of avenues. There are a number of approved therapies that involve combining small molecule anti-angiogenic therapies with checkpoint blockade. In particular, like hepatocellular just had an approval that was kind of transformative at the front line of a small molecule VEGF inhibitor with PD-L1 antibody. So.
Okay, thank you.
Great, I know you had a question.
Yes, my question is also for Mike. So you mentioned about how it's important to understand the origins of the immune ignorance, and you kind of gave the example of beta-catenin and how when you, I guess, introduce it back, you kind of get a better effect. So is that something that's currently being done? And what are the, I guess, cons of that if you're doing a combination therapy where, like the example you showed us? Yeah,
so, the challenge is really, how much can you customize therapy for individual patients, right? Like, so, where the field is trying to get to, but I think is not there yet, is how far can I go with biomarker analysis so that I can really understand at an individual patient level what the barriers are and then circumvent them in a customized fashion. Medicine is still sort of catching up with that degree of personalization. So where we are now, which is better than where we were, is looking at groups of patients. What's the most common sort of mechanism of evasion in, let's say, this particular subset of patients with this specific particular subtype of breast cancer? And then at least I know that's an enriched population for a certain invasion mechanism, let's say upregulation of IDO and tryptophan degradation. So then I can try an add-on trial there. But what Stephanie did in the mice to show it's beta-catenin, and when it's beta-catenin, we need to reinduce DCs. We're really just getting to sort of that level of personalization in patients. We're getting there. I think there are some things associated with, for instance, KRAS mutations that are very obviously immunosuppressive, and people are actually starting to target combinations specifically for patients with certain KRAS mutations. And actually, to get to the earlier, even combining some of the KRAS now inhibitors with checkpoint blockade. But we're not quite there yet. I think it's trying to put in place the type of biomarkers that can be scaled to a large number of patients that will give you that information, and then having therapeutics in place to address those. It's still, that sort of framework is still building at the clinical level.
Hi, Mike. I have a question.
Okay, Kumar, you go ahead, then Harman.
Yeah.
Go ahead, Kumar.
The talk is very interesting. If you block PD-1, will there be any changes in other co-inhibitory molecules like LAG3 or TIGIT? Is there any proven studies?
Yeah, no, it's and I think the tricky part is, we can't give someone 7 antibodies. So which are the really critical ones? And so there's been a couple really promising combination studies, one of which was done recently in lung cancer by Genentech, showing that blocking PD1, or in their case PD-L1, with TIGIT had a very strong additive effect in a subset of lung cancer. And so, I think you are seeing that. And there's another study in melanoma showing the combination of PD-1 blockade and LAG3 has a potentially beneficial effect in melanoma that's probably going to lead to finally a registration for a LAG3 antibody. I think the tricky part is CTLA-4 and PD-1 seem to be somewhat universally relevant, right? They're the go-tos for cancers to shut off the immune system from a checkpoint perspective. A lot of engagement of the others. Where is TIGIT important? For instance, we found TIGIT's maybe very important in head and neck cancer, in lung cancer. Mm-hmm. Where is TIM3 important? Where is VISTA important? Those seem to, at least in some cases, be more, I don't want to say tissue specific, but certain types of cancer, certain tissues seem to engage those secondary checkpoints more. And then, for whatever reason, not so much others. And so I think there's not one answer to your question. It's more a matter of saying, okay, TIGIT's going to be really important in lung, but if I have to choose a secondary checkpoint in melanoma, it's probably not going to be TIGIT. It's going to be LAG3. And if it's prostate, it's probably going to be VISTA, right? And so some of that is just we're doing better science in patients, but the global reach of kind of CTLA-4 PD-1 probably isn't replicated by things like LAG3, TIGIT, et cetera. You're probably not going to have a triple combo that's for everybody with all cancers.
Thank you. And Harman, you've had your hand up very patiently.
Yeah, my question is also for Mike. So it's very popular in drug development when there might be a mechanistic basis to ask if some particular treatment would synergize with the checkpoint blockade.
Right.
And I understand in the past that this term had almost become controversial because of the challenge of distinguishing between the additive and the synergistic effects. I just wanted to ask you what your thoughts were on this and what you think the best or most rigorous definitions of synergy are.
Oh, it's a good question. And actually, maybe I'm getting old. My brain is failing me, but there is that one paradigm for discriminating additive from synergistic where, you sort of got the plot and you can plot. I wish I could, I'm just forgetting the algorithm, but that's the one most of us have used to actually sort of mathematically discriminate synergy. But to some extent, it's eye test, right? When we say CTLA-4 is PD-1 is synergistic, basically you've got some patients who have a 10% response rate to either therapy. You treat them with a combination, there was 50% of them responding, or 45% of them responding. There's obvious synergy there. And it's also, and also when we look at therapeutic synergy in patients, it's not just the percentage that respond. It's a lot about, and this is kind of the subtlety that's sometimes lost in clinical translation because it doesn't come through in OS and ORR as much, but you see synergy in the quality of their responses, right? There's a qualitative synergy that I think we're still trying, to find a way to use as a metric, where I know patients that melanoma patients, for instance, they get CTLA-4 and PD-1, they just do better. Like more of their tumor goes away. Their quality of life is more improved. The responses tend to be more durable. We see less breakthroughs of recurrent disease. This kind of, they develop brain mets less frequently. These kind of things are difficult to quantitate with just those numbers. But I will get back to you. I will think of the algorithm that many of us use for synergy. But really, there is kind of a, you do sort of put it to both tests, the mathematical test and sort of, the eye test. You don't just want to see an incremental improvement, although sometimes incremental improvements are still improvements. When you're looking at 3,800 different combinations of PD-1 in trials, which is going on now, to stand out amongst the 3,800 and reach FDA approval, something magic has to happen, so to speak. And that's what we're looking for. I do want to do one thing. So I don't want to steal from Zubin. There was a really good question for Dr. Zhou. There was a really good question in the chat that popped up about are there ways to reduce the costs of CAR T cells? I'm not going to steal that. I will say I've done some work with some groups that are doing gene therapy based. So, where the patient makes the CAR isn't made externally. But I want Dr. Zhou to have a chance to answer that, because it's really that what holds back CAR T cell therapy is the cost and the personalized effort involved. So I'm gonna let you take that one. I don't want to monopolize the questions.
Yeah, I would just 1 minute, try to keep the time. So I think the major cost is about this is cannot be scaled up. It has to be 25% of the the money actually is it's driven by this labors. It cannot be automated at the current stage, and also they have to be centralized when they were manufactured. So the ultimate solution is if we can do shifting the centralized to decentralized manufacturing, and also can make this process more automated. So this you can do like a bedside manufacturing at the hospital rather than to centralize factories. And the second thing is you can do is to developing some allogeneic products, basically removing the donor T cell receptors, so they will not have the graft versus host disease when they're infused. So basically, it's making them more universal. For example, a healthy donor, you can engineer them and it can be fused into other patients, and then you do not rely on the same patient to extract the T cells and to make CAR T cells from the same patients. Those are the potential solutions for in the long run.
Yeah, and there's some cool stuff going on there. The other one, I don't know if you guys have an NK thing coming up, but
right, CAR NK. We don't have time to mention this. CAR NK, CAR macrophage, CAR M. Yeah. So a lot of other immune cells, CAR NK actually is, can be much less troublesome, compared to CAR T. Yeah.
What I think we might look to is in the coming year, Suzanne organizes monthly workshops, and we can follow up on some of these topics in a monthly workshop on engineered both the myeloid and lymphoid cell systems to do that and delve into this in much more depth. In the interest of time, we probably need to move on. We've got another just a very exciting presentation coming up. There were some questions in the chat room, one for Mike, I believe, on CTLA-4 antibodies, and some suggestions on the synergy systems. I'll let you guys answer that independently, and we'll go ahead. And I know, Kai, you had a question to do that. But what I would really like to do is to move on to the next session. We're very fortunate to have Dr. Ahsan Farooqi from the Department of Radiation Therapy at MD Anderson, who's very generously agreed to join us and give us an overview of radiation therapy and potentially some of the ways that cancer therapeutics and radiation therapy are being integrated to do that. This is an important topic that doesn't get talked about, I think, often enough in the therapeutic spectrum in terms of doing that. So Ahsan, thank you very much indeed for agreeing to join us. And
thank you for having me.
Presentation. Can you go ahead and
yes,
take control of the screen? And thank you.
Great. Can you guys see me and my screen?
Yes, it looks great.
Wonderful. All right. Well, yeah, thanks again, Dr. Davies, and thank you to all the panelists and of course all of you students. I'm very excited to be here to chat about radiation. I do want you guys to know that when we graduate from med school and do our training in radiation oncology, it is a 5-year program, and I have the impossible task of summing all that up in 45 minutes, but I'm going to try my best, and hopefully you guys find this helpful and relevant as you guys progress in your training and in your research projects. And so this is just an outline of the talk. So before we kind of get into how radiation is used clinically, I want to give you guys an overview of how radiation works. We're going to talk about some really quick basic radiobiology, and then the interaction of radiation with chemo and radiation with immunotherapy, which of course is gaining a lot of interest right now, especially the radiation with immunotherapy for a lot of reasons, which we'll get into. And then I'm going to give you guys some examples of sort of how to think about radiation conceptually within the disease types that you all are going to be researching in your lab space. And then we'll sort of summarize everything at the end. So, this is a really important graph that I kind of want you guys to get a really good understanding of early on in this talk. So, what exactly is the therapeutic ratio? So everything from a cancer therapy standpoint comes down to this curve. We know with radiation that we can increase it to a dose that is deadly. Actually, the first time I was interested in radiation oncology as a specialty, I met with a radiation oncologist locally, and he told me, he said, the greatest thing about radiation is that we know that if we push enough dose, that the tumor cells are going to be overwhelmed and we're going to kill it. So we've had the cure for cancer for 50 years. I like to tell my students that. But the problem is we can't deliver those ablative doses because there's, of course, surrounding normal and healthy tissue, and we have to spare those. And so, you have these curves here to kind of show that as you increase the radiation dose, which gives you good tumor control, you're also right parallel to that, increasing your chances for normal tissue complication. And herein lies the problem and where we need to make some advances. So what are some factors that can influence the therapeutic ratio? So the intrinsic radiosensitivity of a cancer cell, some cancer cells will respond to lower doses of radiation, whereas other cancer cells need a lot higher doses. Of course, the anatomy and the proximity of the tumor to the normal tissue, and these are all some things that we think about. So, our goal is to space that out. A better therapeutic situation is when we can deliver a dose of radiation, get 100% chance of tumor control, and accept a very, very, very low chance of normal tissue complication. And of course, when these two curves are very similar, you're not getting that. And you are now in a situation where, you're having a goals of care discussion with the patient. Is it worth doing this because the chances of causing damage is so high? So, I'm sure all of you guys know the DNA structure, but just really quickly. So, basically the DNA is a double-stranded helix, and it's formed by these four sort of building blocks, adenine, guanosine, cytosine, and thymine. And radiation works by damaging the DNA. I mean, it's that pure and simple. You may read papers out there that talks about radiation influencing the protein structure and this and that, but by and large, 99% of our damage occurs because we are damaging the DNA within a cell. So there's many ways with which we can accomplish this. But really the goal is to have radiation enter and deliver the damage selectively within the DNA. Now, I know you guys might think that's impossible, but there are newer forms of radiation therapy with the differing energies, and I don't want to get into the physics too much, but actually where we can accomplish this better than traditional radiation with X-rays. And I'm going to get into some of those various types of radiation technologies later on in this talk. So the unit of cell kill, or the unit of radiation that we use that correlates with cell kill, is a gray. And a gray is basically defined as, the amount of energy that is deposited per kilogram of tissue. And I just want you guys to know that for a single gray that is given, you get over 100,000 ionizations. But of those, only about 1,000 leads to damage to a base in a DNA, and about 1,000 single strand breaks. But those are not enough to kill a cell. It's really the double strand breaks and the DNA protein crosslinks that are going to be lethal. And so you can see that the frequency of those per gray of radiation that's given is much lower. And that's what we are definitely targeting, because that is what is going to become lethal for the cancer cell. So, there are various forms of chromosome type aberrations that, I'm showing you guys here, and I'm going to explain it here. This may be a little bit easier to conceptually understand. But if you have a cell that hasn't replicated its DNA yet, and you zap it with radiation, and you get a double strand break in each chromosome, when that cell tries to undergo mitosis, of course, that genetic information is not packaged properly. And then when it tries to replicate that, you get these fragments. In this case, this is a dicentric and this is an acentric fragment. And so you get misassortment of the genetic information, and this is a lethal aberration. You could also get it in a single chromosome, and which can then form a ring, and this is also lethal. Or you could get, within the same chromosome on different chromatids, you could have a double strand break, and then when it tries to repair it and replicate, you get a dicentric chromatid and an acentric fragment. And the reason I'm pointing these out is because in the early days when we were understanding radiobiology, the scientists, this is what they were doing. They were doing mitosis spreads after giving radiation, and that's when we were identifying that, hey, in the cells that are dead, you are seeing these lethal type aberrations. And this is the main way that radiation exerts its damage, again, within the cancer cells and of course the normal cells. It's these double strand breaks that then lead to misassortment of genetic material that the cell can then, of course, after dividing, cannot survive. So relevant to what some of you sort of wet scientists are going to be doing in the lab, like how do we quantify radiation induced DNA damage? One of the earlier ways or earliest techniques that we did this was doing pulse field gel electrophoresis, where you would irradiate the cells, embed them in these agarose plugs, and then of course apply the differential electric fields and see how the DNA fragments migrate. And when you saw essentially smaller fragments that migrated less, you would then know that you had DNA damage. But now we have newer techniques. We have the COMET assay, which is a favorite way of sort of looking at DNA damage induced by radiation. And the principle is the same, but basically you take the nucleus of a cell after it has undergone radiation and you embed it in this gel. And of course, if you have fragments of DNA due to DNA damage, you're going to see that the DNA is not intact in the cells undergoing radiation. In this case, it was given 10 gray of radiation. You can see this tail, which resembles a comet, that indicates smaller DNA fragments due to DNA damage. And when we look at what happens after a cell gets radiation, another very commonly used assay that I'm sure some of you guys have done in your labs is looking for gamma H2AX foci. So when the DNA is damaged, one of the earliest pathways that's activated is the ATM and ATR pathway, and it signals a phosphorylation cascade. And one of the things that's phosphorylated is the histone 2 marker on the DNA cells and the chromatin itself. And so you can see that when you give 10 gray of radiation and do an immunofluorescence experiment where the antibody against H2AX is labeled, you can see that within the nuclei now, you have a very, very heavy gamma H2AX signal, suggesting that DNA damage has taken place effectively. Now, I do want to say that this is not informative in the sense that if you take any cell, whether it's cancer or not cancerous, and you subjugate it to radiation and you do this experiment, it's always going to show this gamma H2AX signal. So really the best way to carry out these experiments is actually to treat the cell with radiation, get a basal read of how much damage there is, but then measure it again 24 hours later or 12 hours later to see how much of that has been repaired. And in the cells that have a very effective high repair capacity, you're going to see a lot of this disappear. And in the cells that have defective DNA repair, you're going to see the signal persist. So it's really a time course experiment that is needing to be done that will really get you to understand the radiosensitivity or the radio-resistant nature of a particular cell type. So I don't want to spend too much time on this, but what we're taught as radiation oncologists are these 4 R's of radiobiology. And so I just want to really quickly, briefly go over when we look at understanding how our radiation is able to target and kill a cancer cell, we look at these 4 factors. The first one of which is repair. Of course, if you have a cancer, and this is actually the area of research that I'm interested in personally, but you have different cell types, each with different repair capacities, and you have different types of damage. You have those DNA strand breaks, like I mentioned earlier, that lead to lethal aberrations. And so that kind of damage we can summarize as a lethal damage. But you also can have a lot of radiation-induced DNA damage, such as single strand breaks and base damage that can be repaired. And so there is a time component, because if you have a cell type that has a very good effective way of repairing single strand breaks and base damage, those cells are able to essentially repair the sublethal damage, which in other cell types would become lethal if enough time is given. So an example of this that I want to give you guys are BRCA mutant breast cancer or ovarian cancer cells. So they have an inefficient way of repairing single strand break damage. And so when we combine that with radiation, there is some synergy because the sublethal damage that's given from radiation is not able to be repaired. And so these are really the 2 main ones. The potentially lethal damage is essentially more of like a time factor, in the sense that maybe some cancer cells are able to repair their DNA within minutes to hours and others need more time. And so potentially lethal damage is more of a time factor, not so much of a radiation factor. Then the other R of radiobiology is redistribution. What that means is depending on what cell cycle the particular cell is in, it can be more radiation resistant or more radiosensitive. So we know that late S phase cells are the most likely to survive radiation, because it's during late S phase that you have homologous recombination very active, and that's the most efficient way to repair double strand breaks. So it is important to know that depending on which phase the cell cycle is in, you can have differing responses to radiation. And oxygen plays a big part in this too, because radiation, when it is given, it interacts with essentially any molecule. And if you have a high amount of oxygen tension, you can actually generate more secondary hydroxy radicals, which can then cause damage. So if you are taking a cell line and you're incubating it in your 20% O2, and then you're giving radiation in your lab, you can expect there to be a lot more radiation damage compared to if you have a similar cell type that's only in maybe 5% oxygen in a more hypoxic environment. So that's something for you guys to think about too as you do these experiments. And the last R is repopulation. And basically what this means is, paradoxically, radiation can trigger a repopulation or a growth of cells, because the cancer cells maybe are not growing as efficiently, and you give radiation and you just sort of stimulate maybe a niche of cells that realize that, hey, we're being hit, we have to grow. And so this phenomenon we see in clinic all the time, where we start a patient on radiation, a few weeks go by, and we actually see a growth while they're on radiation, which of course is scary, but that's usually just a temporary thing. And then in the long term, we get the cell kill and the treatment that we desire. So cell survival and how we measure it, it's a little bit different in radiation compared to standard chemotherapy. So we know that radiation can kill a cell, but we also know that radiation can do different things. You can affect a function of a cell without necessarily killing it. An example of this is, maybe cells in the pituitary gland that secrete hormones. It's going to take a lot of radiation to kill those cells, but by giving 2 or 10 gray, you can actually suppress the function of it. So that's also something that we have to, take into account. But one important thing that I want to talk about here is this concept of clonogenic cell growth. So radiobiology is defined as the amount of radiation that gives you a tumor control probability. And we want to achieve maximal tumor control by reducing the amount of cells that have a clonogenic potential. So we don't want any cell, like you could kill 99.9% of cells in a tumor, but if that one cell is left behind 1 or 2 or 3 years later, it could begin to grow again if it has clonogenic potential. And the way we do this in the lab, and what some of you guys might have done if you've done radiation experiments before, is this assay called the clonogenic assay, where we assess the clonogenic potential of a cell line after radiation, and where we give differing doses of radiation, and we quantify the amount of colonies that are then able to form after certain amounts of radiation dose are given. And so you can see here's your control cell that wasn't given radiation. And in this experiment, we were comparing the efficacy of 2 grays of standard radiation and 2 grays of proton radiation. And you can see that the cell type was more sensitive to the proton radiation, and that there's less colonies that were formed. So another common, I guess not mistake, but misconception about radiation is that radiation actually does not cause cell death through apoptotic mechanisms as the mainstay. So certainly, yes, apoptosis is part of it. And some cell types, such as lymphoid cells, are very, very, very prone to apoptosis after radiation. But the vast majority of cancer cells and those tumors that are not derived from lymphoid cells actually die via mitotic catastrophe. And so when I see papers and when I review papers where radiation's given and they say, look at the apoptosis, it wasn't different, therefore radiation wasn't effective, actually it could just be that that cell type wasn't predisposed to dying via radiation-induced apoptosis. So if you're ever doing these sort of experiments, make sure to keep that in mind, that radiation-induced apoptosis is just maybe accounts for about 20 to 30% of the cell kill, but in reality, it's mitotic catastrophe that drives this. So that's just like basic radiobiology. And now what I really want to get into is, combining radiation with chemo and with immunotherapy. So, what we want to see is when we have a particular cell line, and here is a survival curve of giving radiation, we want to give maybe a radiosensitizer or a particular chemotherapeutic agent to shift this curve this way, and so we see more cell kill. But that's actually very, very difficult. This sort of synergy is very rarely seen, and most of the time, what we actually see is just a loss of the shoulder, but not a huge shift of the curve, but more of just a displacement of the curve. And when we go into understanding, how does radiation work with chemotherapy, you're thinking about, lots of things. Of course, radiation is a targeted therapy like surgery. We're pointing our beams at the cancer, whereas chemo is in the blood. So, of course, the biggest advantage of chemotherapy in the treatment of cancer, unlike radiation and surgery, is you're able to eradicate micrometastatic disease. But the other way to think about it is, what if we do both together? What if we give both radiation and chemotherapy together? And that can really, potentially sensitize the tumor. And we do that a lot. We do concurrent chemoradiation in head and neck cancer. We do it in lung cancer. We do it in gynecologic cancer. And a lot of trials have established that doing both together are actually better than just doing one or the other. And so when you look at the agents that are commonly seen, definitely cisplatin and 5-FU are the two most common chemotherapies given with radiation. We're definitely scared to give anthracyclines and gemcitabine and dacarbazine. You've seen a lot of toxicities with these. And some of the other ones, such as topoisomerase inhibitors, maybe those that affect microtubule formation, those we see some synergy, but not that much. So this is sort of like the main two drugs that we combine with radiation in the clinic. And so, what are some ways that they can synergize? I think the biggest take-home point here is, if you have a chemotherapeutic drug that damages DNA and radiation damages DNA, those are definitely the most common types of synergy mechanisms that we see. And you can actually also look to target the DNA strand itself. So this is just an example of a compound called halogenated pyrimidines, which essentially make the DNA more bulky. And so when you give that with the radiation, you just have an increased chance of having DNA breaks, which can then, of course, result in more lethality. And then two other approaches I briefly want to mention are sensitizing hypoxic cells. So this is a drug that we have a lot of excitement with currently, called Nemorazole, because it specifically goes to cells that are hypoxic. And like we mentioned before, hypoxic cells tend to be more radiation resistant. And we actually have clinical data that suggests that if you give Nemorazole with radiation in head and neck cancer, you can actually improve local regional control and survival. And so this was a landmark study that showed that clinically targeting hypoxic cells in combination with radiation is doable. And so we are building upon this right now in the clinic. And then lastly, along with the targeting hypoxia, let me just skip ahead to this slide here, which really talks about the reverse aspect, which is, how do we protect our normal cells with radiation? There actually is one drug that is FDA approved that we use in the clinic, and that's called amifostine. It currently remains the only FDA approved radioprotector, but the idea is it's taken up selectively in the normal cells and less likely in the cancerous cells. And it can scavenge free radicals that are generated from the radiation. And so we do, or we can give it to prevent dryness of the mouth when we do head and neck radiation treatments. We can also use this to protect the kidney, especially in patients that get cisplatin, which we know is toxic to the kidneys. So, this is just sort of looking at how much protection is given. So you can see here that amifostine is, better able to protect the bone marrow and the liver. This probably has to do more with the pharmacokinetics of this drug and where it goes. So an area that's getting a lot of excitement recently is combining radiation with immunotherapy. And I know as part of this course, you guys are learning about all the various advances in immunotherapy. And so radiation does have a role. So if you just want to look at immunotherapy by itself, it's basically you're revving up the immune system. And I'm not an expert in immunotherapy, so you guys can definitely look at your other slides from the immunotherapy experts. But basically there's checkpoints that can downregulate our immune system. And so of course, Dr. Allison identified CTLA4 as one of those checkpoints, and we now have a drug that reverses that. Essentially what this does is it increases the T cell activity against the tumor. And we know that this has been shown to be very effective. And the first trial, where it was done, it was actually in melanoma patients. And we still, are using this. We're using other drugs such as Pembro, Nivo, which target a different checkpoint. And then the latest generation are PD-L1 inhibitors. And those are Atezo and Durvalumab. And I'm just showing this here because this trial was published recently in the last 3 years in 2017, showing that in lung cancer, when we give chemotherapy and radiation and nothing, the survival is close to 25%. but now it's standard of care to give durvalumab after giving chemotherapy and radiation. And you can see a huge shift in the survival curve here, suggesting that durvalumab is very, very effective at preventing, of course, the cancer from recurring. So how does radiation work with immunotherapy? If you give radiation, you're causing DNA damage. And when you're causing DNA damage, you're releasing the inner contents of the cancer cell. And that's really important because that can then go to your bone marrow, to your spleen, to your thymus. And those fragments are essentially antigens, which the immune system can then learn. It'll recognize these mutant antigens that are not present in your normal cells. And then you can use your immune system to attack radiation. Now, unfortunately, this is like the beautiful gold standard scenario that we're all taught. But the reality is radiation also can kill these exact immune cells that are trying to kill the cancer. So it's a balance. So you want radiation to kill the tumor and expose the antigens, but at the same time, you don't want to give your radiation in such a way to where you're depleting the immune cells from getting their job done, of course, which is to kill the cancer. And so there's a very elegant experiment that was done that I'm just going to show here, where you can see if you give a certain amount of radiation, in this case 30 gray, in a single fraction, and you do a very good job about sparing maybe the immune cells with the way you're modulating and targeting the beam, you can see that the survival in patients, or not in patients here, this was done in mice, is very good. But when you do that same dose and you break it up and you do fractionated radiation and you give it with immunotherapy, you can see that you're not really getting that same effect because you're probably killing the immune cells that you're trying to rev up by giving the immune therapy. So this is something that we're trying to be more mindful of in our clinic. We look at the bone marrow, we look at areas where there's a high likelihood of there being immune cells, and we're trying to limit our dose. That's not really something that we would think about 10, 20, or 30 years ago. And so really the last part of this talk, and I know I've been talking really fast here, I just wanted to make sure I left enough time to really get to this, because I think this is the area that, of course, unless you're in the clinic, you're not really being exposed to on a day-to-day basis, which is how radiation is used in different types of cancers in order to achieve tumor control. And so this is like a very broad stroke. I don't want you guys to kind of look at this as like, hard and fast rule. But when we think of radio resistant versus radio sensitive histologies, I really want to drive home the fact that lymphomas definitely are the most radio sensitive histology. And I think a lot of that could be due to the fact that they have an intact apoptotic response to radiation. And just to give you guys an example, if you have low-grade lymphomas such as follicular lymphoma or malt lymphoma, we can actually get about an 80% cure rate with just 4 grays of radiation. And that's huge, because for some of these other intermediately responsive to radiation cancers such as lung or colorectal, we need upwards of 70 gray to achieve a response. Even these HPV positive head and neck and gynecologic malignancies such as cervical cancer, anal cell cancer, you need upwards of 50 to 60 gray. But really, with some forms of lymphoma, 4 gray is enough to achieve a good response. For Hodgkin's lymphoma, which we see a lot, 20 to 30 gray is enough to get a full 95% overall survival. So there is this huge spectrum. And when I do collaborative experiments with the surgical oncologists and medical oncologists here, they always ask me, they say, hey, what dose of radiation simulates what you see in the clinic? And I'm like, that is a very loaded question, because it just depends from cancer type to, of course, what the goals of care are. So there isn't really a good number for me to tell you guys, but certainly I think for in vitro experiments, if you guys are doing them, I think a range of 0 to 10 gray is appropriate. And then the intermediate sort of responsive to radiation histologies, those are your more common ones. Breast, prostate, lung, of course, are the 3 most common cancers we see, colorectal as well, hepatocellular cancer as well. And then the radiation resistant histologies are, of course, melanoma, sarcoma, and glioblastoma. And melanoma and sarcoma is actually what I'm specialized to treat here at MD Anderson. And so, what I am doing in my clinic is very different than what some of my colleagues who treat head and neck and gynecologic malignancies are doing in clinic, where they are really able to achieve a cure with radiation by itself, whereas my role in melanoma and sarcoma is more in the adjuvant setting, which is what we're going to get into. So when you're thinking about radiation, you have to ask yourself, what is the intent? What are your goals of care? So, these are sort of 5 different ways that we like to conceptualize our radiation technique. The first term I want you guys to understand is definitive radiation. What are we trying to do with definitive radiation? We are trying to ablate the tumor. So surgery is not an option. Chemo may be given, but really we are the definitive local control option for this patient. And so here we are trying to take it to doses to where we get upwards of 80 to 90% chance of tumor control. So that's one example. Consolidative radiation is what we're trying to do here is we're trying to, so you have a patient that gets chemo, the chemo has done a good job, it's weakened the tumor, it's killed the tumor, and now we're trying to add on top of the chemotherapy and make sure that we keep the tumor from growing. So that's the goal in consolidative radiation. Palliative radiation, I mean, the answer is in the word itself. So the goal here is really to help provide symptom relief. And this is a good chunk of who we see in clinic. About 25 to 35% of our referrals are really, patients who don't have many good options left, and we can still be very effective by giving a local dose of radiation, helping these patients achieve pain. Maybe they have bony metastases, maybe they have difficulty breathing or difficulty swallowing, and we can provide some targeted therapy. But now we're not looking to dose escalate. And then the last two, basically it just differs in that is radiation given after, in which case, or after the surgery, in which case we call adjuvant radiation. And if the goal is to shrink the tumor so that the surgery is more easy, then that's called preoperative radiation. And the way we can do that is with many different techniques. So the first sort of way radiation was given back in the 50s and 60s was external beam radiation. That still is one of the main ways we give radiation. And usually the source of radiation is photons or standard X-rays. But there are other techniques. One way that's very effective is brachytherapy, and we can actually order radioactive seeds and implant it into the cancer. I'm going to show you guys a picture here pretty soon about how we do that in prostate cancer. We can do external beam radiation with not X-rays. And so we at MD Anderson have something called a proton center, a proton machine. There's one of only 2 in the state. And there's differing properties of protons versus X-rays, which again, I'm going to get into with illustrations. And then there's some excitement about using other heavy ions, such as carbons, neutrons, and helium therapy. And then gamma knife radiotherapy is something that you guys may have known, but basically that's using a live source of radiation from cobalt-60. And we do this for patients who have brain metastases, and we have them come in and we put a shell on their head. And there's about 180 holes, and this cobalt radiation comes through all of it, and it pinpoints itself on the brain metastatic lesion. So there's different technologies that we have to achieve our goal. There's not just like a one-size-fits-all approach. This is a picture of a patient who has prostate cancer, and what I'm showing you guys here is this is a sagittal image, so you're looking at the patient from the side. Here's the end of the spinal cord, so this is the sacrum. The yellow is the bladder. The green is the rectum, and the blue is the prostate. So you can see the difficulty that we have. How are we supposed to get a dose of radiation in to kill the prostate cancer while sparing the rectum, while sparing the bladder? And so this is the illustration I was referencing earlier. So photon radiation, which is your X-ray radiation, is seen here below. Sorry, this is labeled incorrectly. This should be here on this side. But you can see with photon radiation that you can get an ablative dose to the prostate, but you have a lot of scattered dose. You're giving this patient a dose to the bladder, to the rectum, you're giving this patient a dose to the femoral heads. But now with protons, which allows us to come in and stop, you can come with 2 opposed beams and you can spare a lot more of the normal tissue. So there's 0 radiation going here to the bladder. There's 0 radiation here going to the posterior half of the rectum. And so now, with this technology, we can do more targeted treatments. Another role of proton radiation that we see a lot in clinic is in pediatric malignancies, especially when we're treating the brain. When we're treating the spinal cord, you can just come in from the back, deliver your dose, and you don't get that exit dose. So I just want you guys to be aware, because this is probably something that you're going to see more and more centers developing these proton centers. And so there's a lot of excitement about doing proton radiation with chemo, with immunotherapy, because we didn't have these tools before. Maybe protons can be used to spare, like I said, the bone marrow and preserve our immune cells more if we're trying to do radiation in combination with immunotherapy in the future. This is an example of a brachytherapy seed implant. So again, the goal is to get an ablative dose to the prostate, but in this case, we're not coming from the outside. We're actually coming from the inside. We have these patients who come into our OR. We put them under anesthesia, and we use a template, and we order seeds, and we inject the seeds directly into the prostate. So it takes about 3 months for the dose to deposit, but it's very effective, and it has a prostate cancer cure rate of upwards of 95%, which is great. So it's equivalent with the external beam radiation technique, but the difference is it's done in 1 day. So a lot of patients do like this option. This is an example of palliative radiation. So like I said, a bone is one of the most common places that we can see cancer spread to. And so this is an example of a patient that I treated that had metastases to their cervical spine. And really the goal here is not to deliver 70, 80 gray. So it's maybe a little bit hard for you guys to see, but the dose of radiation that we're giving here is actually 30 gray. But that's very effective. We have 80% chance of controlling this patient's pain just by giving 30 grays of radiation. So, for a lot of these patients that are, moving to hospice, the medical oncologists send these patients to us so we can maximize their pain relief. So there are, other times we think of radiation where the goal is not just about curing the cancer. It's also about providing relief. This example of a 70-year-old with left lower lobe lung cancer, you can see it here on these two CT scan images, measuring about 6 by 6 centimeters. And I really like the slide because it again points to one of the advances that we've had in radiation, which is on the physics side. So when you typically get a CT scan, the patient is just breathing. And of course, the tumor can move every single time a patient takes a breath. And so we can now do special CT scans where we can track the movement of this tumor. And we can make sure that our radiation fields are encompassing the entirety of the tumor as it's moving when the patient's breathing. So in the past, we couldn't do this, and we probably were missing a lot of the tumors on the edges, or a lot of the tumor cells, whereas now we can do a more targeted therapy. So this is an example of what a radiation plan looks like. And you can see here the radiation dose going to the tumor in the surrounding areas is 70 gray. So the intent here is doing definitive radiation. So this is it. The patient's not getting surgery. We are the local control treatment of choice. This patient got this therapy with chemotherapy. I treated him, and he is now currently in remission. When he comes back for his scans, there's just scar tissue that's left here. So, in the absence of surgery, we can still achieve a meaningful control. And then the other two examples that I want to give, and I know I'm about 8 minutes away from my time being up, but is adjuvant radiation and preoperative radiation. So really the best example of this is breast cancer. So in the early 1900s, women who were diagnosed with breast cancer had very, very radical surgeries that were done. The most famous of which is a radical mastectomy, also known as the Halsted mastectomy, because named after the surgeon that developed this procedure. But they didn't just resect the breast; they would have to dissect out the chest wall, the lymph node chain, take out the pectoralis major, take out the pectoralis minor, and of course this was very disfiguring. But that was the only way, because they knew that breast cancer, even though you just saw a lump, it had a tendency to spread regionally. But then with advances in surgical procedures, we can now actually do a more targeted mastectomy where we just take out the tumor and the breast tissue and sample the lymph nodes. And so this is still good, but the patient is still, having to deal with missing a breast and having that asymmetry. So in the 70s and 80s, the radiation oncologists and the surgeons got together and they said, hey, what if we start just removing the tumor, making sure the lymph nodes are negative, and then you guys coming in and doing radiation to the rest of the breast? Can we do a breast sparing approach in these patients? And the answer is yes. All the trials have now shown that in the absence of a mastectomy, you can take out the tumor itself, and we call that procedure a lumpectomy, give radiation. So this is an example of a treatment plan where we come with two opposing tangents, and we treat the remainder of the operative bed and the rest of the breast. And the survival in those patients who get a mastectomy and don't get any radiation, and those patients who have a lumpectomy and get radiation is the same. Of course, the biggest advantage being that in the patients who get radiation, they still get to preserve their breast. And so if you guys were to take a guess as to how many patients opt for the lumpectomy with radiation approach, it's actually the majority. 95% of patients diagnosed with breast cancer prefer this approach over having one of their breasts removed. And we wouldn't have been able to achieve that without having radiation essentially in our toolbox. And then the last example, and this is what I do now, now that I specialize in sarcomas and melanomas, is giving preoperative radiation. So this is a patient who has a sarcoma behind his knee, and you can see here that it is displacing the muscle. Of course, it was causing a lot of pain, and so the surgery, would be challenging. And in the 80s and 90s, when a patient with sarcoma presented to the clinic, the only curative treatment modality was an amputation. So just like the example I gave with breast cancer, you had to do a radical surgery to achieve a chance of a cure. But then the radiation oncologists got together with the surgeons and we said, hey, what if we give radiation before? The first thing is it may shrink the tumor and make your surgery easier. And the second thing is if we treat with the margin, you don't have to do an amputation. We are taking care of the micrometastatic disease nearby the tumor for you. And so there was a few landmark trials that were done, and actually Peter Pisters, who's the president of our institution at MD Anderson, that's how he built his career. He was the lead on one of the 2 trials that showed that radiation with surgery is equivalent to an amputation. And that was done in the 90s by Dr. Pisters himself when he was at Memorial Sloan Kettering. So the last slide, the last point I want to make is, the role of radiation in treating hematological malignancies. So, all the examples I've given before this is when we can see the tumor, which are solid tumors. But we have a lot of cancer types, such as leukemias and various types of lymphomas, where you don't necessarily see a mass, that present to our clinic all the time. And so the question is, can we target those with radiation? And the answer is not really. I mean, those are definitely managed 99% by medical oncology, because it's hard for us to, of course, track a tumor that's floating around in the blood. But that's not to say it's never been done. And we do have a hematologic group here that does these treatments. And so whole body radiation is done. We do this. Of course, it's low doses, because if we were to give the whole body higher doses of radiation, that would be lethal. But we do whole body radiation when they are preparing the patients for an autologous stem cell transplant. And we can hit the sanctuary sites, so where the chemo is not going to be penetrant, such as the testes and the CSF. So we do this in clinic. And then the other example is if you have leukemia patients that have a dissemination of their disease into the spinal cord and in the fluid, the CSF that surrounds the brain and the spinal cord, we do give craniospinal radiation. I know it sounds really toxic, and it actually is very toxic, but it's very effective. And so when this is the only or the best way at preventing cancer from progressing within the brain and CSF, we do craniospinal radiation, both in this setting and also in various pediatric cancers that tend to go to the spinal cord and brain. So, just to summarize here in the last 2 minutes, radiation's been around since the 1950s. And the main way that we exert our, treatment efficacy is by damaging the DNA, pure and simple. So because of that, you can combine, radiation with chemotherapies that also damage DNA and get a synergistic effect. So we talked about cisplatin and 5-FU. But you can also combine radiation with immunotherapy, because immunotherapy doesn't work by damaging DNA, but radiation does. And so when you damage the DNA and you kill the cancer cell, you can get neoantigen presentation, and that can synergize with immunotherapy. It's a common myth that radiation is not going to be needed in the future. When I was in medical school and I told people I wanted to do radiation oncology, that's what they said. They said, why are you doing this? And ever since I've graduated and done residency, the amount of radiation patients that we've treated at our hospital has increased by 40%. Because there's more and more and more of a role for radiation as we're understanding cancer biology better, and as we're making advances in physics and radiation biology. Radiation can be given in many ways, both externally and internally. It can be the sole therapy for the management of solid tumors, such as prostate cancer, head and neck cancer, gynecologic cancer. But other times, we give radiation in the preoperative setting, such as sarcomas, or postoperatively, such as breast cancer. And then lastly, the use of radiation, of course, in leukemias and some forms of lymphomas is limited, of course, because of just the nature of the tumor, but we still do it from time to time. So I just want to wrap up by saying thank you again for having me. I want to give Dr. Stecklein, one of my colleagues, a shout out because a lot of the radiobiological slides he lent to me for this talk. And I want to make sure that I give you guys some time to ask questions. So thank you.
Ahsan, thank you so much. That was just fabulous and presented just the sort of overview that I was really hoping you'd deliver. So I'm most appreciative. And we have about 15 minutes till the next presentation is scheduled. For those of the participants who need or want to take a break, you're welcome to do that, but let's open it up for questions and discussions. Maybe you could release the screen
Absolutely.
so that we could see the gallery. There we go. So we can see everybody and ask who's got a question. And Anu, you have a question and issue you'd like to bring up.
Okay, yes, I do. So my question is, we've heard over the last couple of days the importance of AI and computational biology and things. So I was wondering, is there a role for that in radiation therapy? And what are your thoughts?
Oh, absolutely. That's a great question. AI is making a huge impact. So we have a few, let me give you a few examples. So one of the ways that we're leveraging artificial intelligence in radiation is actually by helping with our treatment planning. So we have a whole department that's interested in researching ways where they're learning how we as physicians contour tumors, normal structures, and then we have machine learning sort of make a pattern out of it. And when I first started residency, I would have to go and like draw the lung on every slice and the heart. And just in 5 years, now when I load a plan, I hit a few buttons, I run a script, and we have a whole atlas now of anatomical structures, lymph node regions. So that's definitely a way in which we are making advances in the delivery of radiation, especially in third world countries. So we have a partnership with a lot of radiation departments in Africa and in Asia, where they are looking at our data of how to contour, and we're sharing that with them. So when they do a CT scan on a patient and pull it up, they can hit a button and it'll actually generate a plan for them based on what we do here. So that's something we're doing. Of course, another newer form of technology that we have here that we're very excited about is MRI guided radiation. So every image I showed you guys here before was based on a CT, but we now have a MRI linear accelerator at MD Anderson. And the reason why that's so important is, of course, MRI gives a different level of detail compared to a CT scan. And so we're doing something where every single day when a patient is coming to be treated, the MRI is done and we see the tumor, and the AI technology does an adaptive plan. So every day, the delivery of the radiation is different depending on what anatomy is seen on the MRI. So we have a lab here for any of you who are interested. Dr. Cliff Fuller is sort of like our main faculty member that runs our AI and MRI guided and a lot of that. So it's not really a wet lab, but he has a lot of physicists. And so, yeah, I mean, that's a great question. I didn't have time to talk about it today, but there's a lot of advances being made on that end. I hope that answers it.
Do we have additional questions for Ahsan?
Yes, oh, sorry. Yes, I have. I'm just curious, based on what criteria you decide the dose for the patient and how many doses you're gonna do?
Yeah, that's another great question. So pretty much when radiation came in the 50s and 60s, trials were done that established those doses. So I'm not really, like 90% of the time, it's set because a certain trial was done that suggested this is what we need to accomplish our essentially goal. So from time to time, I do have to, like, it is an individual decision in the sense that I have to decide how aggressive or how less aggressive to be. But for routine treatment of breast cancer, lung, sarcomas, everything that you guys hear about, those doses are actually set in stone based upon randomized trials that were done back in the day. So let me give you an example. So for lung cancer, in the 80s and 90s, they thought 60 gray was the target, and we did it. And then there was a group of people that thought we could go higher. And so they did a dose escalation trial because there were a lot of people that wanted to do 75, 76 gray. And they did a trial of both where half the patients got 76, the other half got 60. And those that got the higher dose actually had a worse survival. So then we learned that, okay, we're taking these patients to a higher dose, but we're now causing cardiac toxicities. And when the trial came out, it was shocking because we all thought it was going to be positive. but it ended up being the survival curves were flipped, that the higher dose patients died more. And so now we know that the standard of care dose is 60. So it's all informed, all of our dosing based upon randomized double-blind, or not double-blinded, but randomized clinical trials.
Oh, thank you.
Yeah, you're welcome.
I had a question to ask in terms of the hypoxia. It's always been very interesting that the radio resistance is tied to hypoxia. And within tumors, there's presumably a gradient of oxygen delivery. And how does that factor into your thinking about either the doses you deliver or the drugs that you might want to use in combination to address hypoxia?
Definitely. So we know that within the tumor, the hypoxic cells tend to be centered in the very center of the tumor. And those that are kind of in the periphery have more access to oxygen. So what we try to do is we build in a hotspot, Dr. Davies, within the center of the tumor. So one thing that we are doing, if we can safely accomplish it, is, for example, if the patient is required to get, for example, 50 gray to the tumor, we'll have our machines planned to make sure that, the 50 gray is covering the entirety, but in the center of it, that center core, I heat it up to 60 and 70 because I know that you need a little bit more. So we do take that into account that way.
Right. Thank you.
I have a question. I was curious about the seed strategy for prostate cancer. Are there any other tumors that's a possibility for?
Absolutely. So gynecologic cancer, so cervical cancer, we do that. In that case, we don't implant a seed. What we do is we bring the patient into the OR and we put in a device, and the seeds are carried in through a wire, and they go and they stay for a few seconds in the patient, and then they come out. So it's not a permanent seed, it's a temporary seed. And we call that a temporary implant, not a permanent implant, but the idea is the same. And so that's the standard of care for essentially any stage 2 or greater cervical cancer, is we do 4 weeks of radiation, and then we bring them into the OR and give a boost. And so really what we're noticing is that the cancer types that are driven by HPV tend to be very, very sensitive to radiation. I think that could be because the P53 and the RB pathway is, messed up with the, just the virulence of the papillomavirus. And so when we take those tumors upwards of 80 gray, our chances of control are very, very good. So 90%. And of course, the patients that we can't do the seed implant for any reason, those patients, don't do well because we can't get that boost dose. Yeah.
I have one question.
Yeah, go ahead, Priyanka.
Yeah. So we know that the survivors from the breast cancer and the lung cancer, they have a high chance of cardiovascular disease. And because of the radiation, they can induce the senescence in the cardiovascular system. So how do you manage that? How do you control that?
Yeah, that's a great question. So, back in the day when we did the breast cancer treatment, the beams would come very close to the heart. So one thing that we do here at MD Anderson is we have the patient taking a deep breath, and we've seen that it pushes the heart away and to the left side. And so whenever there's a left-sided breast cancer patient where we know the cardiac dose is going to be high, we actually have them hold their breath for every treatment, and we factor that into our planning. Other ways that we're doing it, there's actually a lot of excitement about doing partial breast radiation. So, the picture I showed was whole breast. So again, that was done because the early trials targeted the whole breast, but now the breast community is just doing the tumor and just a little bit of an area outside of it, so about a centimeter. So
okay,
yeah.
Thank you.
Ahsan, thank you very much. It looks like you have a phone call to deal with, but I really can't thank you enough for taking the time. And I'm sure folks who have additional questions will be reaching out to you, but
of course,
I really appreciate it.
Happy to answer any question. Thank you guys so much.
Great. We have a few minutes. Dr. Chapkin, I see, is online here. We'll start at 11:15 if that's okay with everybody. So we have a few minutes of break before we hear Dr. Chapkin's presentation on the topic of chemoprevention. So we'll reconvene at 11:15 for those of you who want to take a break.
Okay, I guess we're ready to get started with our next session.
Hi, Suzanne. Sorry.
Okay.
Great. It's really a great pleasure to present Dr. Robert Chapkin, who's giving the third presentation of the morning. Dr. Chapkin is a professor in the Department of Nutrition at Texas A&M University College Station campus. Dr. Chapkin has been a champion for cancer prevention research and the importance of looking at many aspects and strategies for intervening before pre-malignant conditions develop into fully fledged cancers. He's looked at the nutritional components associated with that, behavioral components, and also potentially the application of chemoprevention strategies. His particular areas in the area of colorectal cancer, where he's a leader in that field, but I think the principles that he can talk to us about today have applications across a broad spectrum. So it's an important aspect when thinking about cancer therapeutics, not only to think about what can I do to treat an advanced established cancer, but even more important is how might we be able to prevent that cancer from developing. So Rob, thank you very much for joining us today, and I'll turn it over to you for the presentation.
Thanks, Pete. Maybe I'm just gonna share my slides again. Where did they go? Where are my slides? I don't see my slides now. One sec. Let's must have closed the file accidentally.
Because they were up just a minute ago. I saw.
Yeah. Unfortunately, I was muted and had to unmute myself, and that caused me to take them down. Now, where did I put these things? Sorry. Here we go. This is typical stuff, right? There we go. That looks like let me just close this and go back to too many windows here. Screen share, and there it is. Okay, open this up, and can you see that okay now?
We're good to go. That's just great. Thank you.
All righty. Thank you. My apologies for the technical difficulties. Hi, everyone. I'm Rob Chapkin. I'm up here at Texas A&M in College Station, and I'm going to give you a little crash course in on what we'll call chemoprevention. And I thought I'd start with one of the major proponents of this field, and that would be Bert Vogelstein. And he wrote back in 2012 that if the current trends continue, the number of cancer cases diagnosed annually by 2050 is likely to double as a result of population aging. So if we as a society hope to head off the coming storm, we better get more serious about cancer prevention soon. And I think that's definitely true to this day. And later on in an editorial in Nature, prevention is as good as a cure. So that's the theme for today. And hopefully I can convince you that it's a worthwhile endeavor. So I'm sure some of you don't know, but this is from a 2018 Science paper that cancer death rates could be reduced by 70% around the world, even without the development of any new therapies. So that's pretty amazing. Think about that. And the NCI has created what they call a triad of interception research that I'll be talking about today, dealing with prevention itself, early detection, and early intervention. So Vogelstein's referring to all three of these in his article. And you all have a copy of this, so you can go read these papers in your leisure later. So it'll be a bit of an onslaught today. And my focus is primarily be on the molecular basis for dietary chemoprevention. That's my real field of interest and my love, my passion. So this is the field, according to NCI. Everything you see on it, this is prevention, chemoprevention. So you may work in some of these areas or none of these areas, but this is their word diagram. And I'll be trying to touch on a number of these components, not all of them. Obviously, there isn't enough time. So hopefully this is making a visual impression on your subconscious right now. One of the challenges to chemoprevention is really nicely shown in this slide, which shows you basically, this is colorectal cancer, the evolution over time. And as Pete mentioned to me, you probably should touch upon this component because it's not necessarily well appreciated. But if you're going to study colorectal cancer as an example, and many other cancers share this, there is a huge time frame we're looking at, actually approximately 20 years in this diagram. From its from normalcy through the very early steps. Here you see some genetic alterations that are occurring. And if you're going to study this until you get cancer and even metastasis, you got to monitor people over 2 decades on average. you can imagine that that creates a huge burden. And how do you do that? And how do you intervene in this kind of temporal manner? And another major factor that makes it difficult to prevent cancer, or certainly lower risk of cancer, is genetic heterogeneity, which I'll be talking about. And host microbe interaction is the latest revelation that's occurring. All this creates great challenges to both the therapeutics field, but certainly the chemoprevention field. And I just wanted to show you, so if you're normal, healthy colon or any form of tissue we're talking about where cancer can develop, basically you go through a series of steps, not necessarily completely linear as shown here, but we'll simplify it and say you move from healthy all the way through an initiated step, mild dysplasia, moderate, severe, carcinoma in situ, and then finally an invasive cancer. In the case of colon cancer, that'd be an adenocarcinoma. And then metastasis can occur. And metastasis is primarily what kills most cancer patients, but the primary tumor in some cases obviously can cause that as well. So transforming cancer prevention, this is from NCI. And the key is to target the early prevention of cancer. That's our goal. We want to intervene as early as possible, detect it as early as possible, and that is a challenge. So I'm going to give you a little representation of that now from this nice review article. So here's normal homeostasis. I'm showing you the intestinal epithelium here. This is a colonic crypt. Colon cancer kills a lot of people in the United States every year. So initially, this crypt is normal. The bacteria in the lumen shown here are considered healthy. And then here's some immune function below that in the subepithelial space. All right, that's normal. Then somehow we have an initiation event. This can be through a mutagenic insult. There's a variety of ways this can occur. And again, you are now stimulating a pro-tumorigenic environment, which is made up of basically the infiltration of immune cells, releasing a plethora of cytokines. The epithelium is changed, and you have the formation of an adenoma. This would be basically the early stage cancer developing. And then you can get through a progression stage where basically you can have anti-tumorigenic and pro-tumorigenic events taking place, facing off against each other. Apoptosis, as an example, programmed cell death can be upregulated to try to delete the damaged cells. And then you basically, the cancer will win out at some point in many cases. And you get all of these molecular events that take place. You get invasive carcinoma, metastasis eventually shown here. And you can spend many years studying all of these events. And I'm just presenting them to you to really show you that if you are intervening at any of these steps, the biology is continually changing and the challenges and landscapes are changing depending on the cancer. So this is very, very complex. Now, one interesting thing to point out is that many chronic diseases, and certainly cancer is one of them, chronic inflammation is a byproduct that is impacting the disease. So the immune system is changing, cells are changing, in this case, epithelial cells. The microbiome is changing in response to markers of chronic inflammation. And chronic inflammation, as shown here in this summary diagram, will impact really all bodily function, but we're going to confine that to cancer here. So I'm basically showing cancer is impacted negatively by inflammation. That's why in some cases, anti-inflammatory processes, invoking them can have remedial effects in some contexts. So just keep that in mind as we get deeper and deeper into this story. And one byproduct or one major disease onset that drives chronic inflammation is your friend obesity, which of course is at epidemic proportions in the United States and around the world now. It causes systemic inflammation. And I'm not really going to go into details on that, but basically wherever you have obesity, you're going to definitely create the promotion of cancer. And obesity, of course, is a diet-related disorder. So just keep that in mind. And here's just some NCI documents showing you that being overweight increases the risk of 8 types of cancer, and they're listed down here. More than 2/3 of those diagnosed with certain cancers are overweight or clinically obese with a body mass index, in this case above 30, overweight above 25. So this is a fact of life, and this is relatively new in the American chronic disease scenario, meaning as of about 25 years ago, there is a big shift, and Americans got basically more and more obese. And before that, obesity was always a problem, but much, much smaller scale. So the genetics haven't changed, but the obesity has. And this just is from cancer prevention research showing how people are trying to target chronic inflammation and looking across all of these cancer types. So this information isn't terribly helpful, except to say a lot of people are very concerned about obesity and how it impacts risk of cancer, many types of cancer. And the NCI is equally interested in these. And so this is NCI information here on prevention interventions. So I'm just going to introduce them to you now. Medications are part of that armamentarium, and therapeutics is definitely being discussed as part of your training. So you'll learn more about that. Lifestyle choices is also a big part of this now. Obviously, the most obvious, quitting tobacco, but now avoiding obesity and obviously any unwanted exposure to carcinogen. Treatment for infections, I'm not going to really talk much about that, but chronic infection can drive cancer in certain contexts, and some of them are shown here. Screening tests, this is the early detection part of it. Vaccines to protect against certain infectious components that will drive cancer in some contexts, and of course surgery. So we have, what do we have? 6 different arms of investigation. And Philip Castle is the current director of the Division of Cancer Prevention. So their NCI has a division, and it's cancer prevention. And what I've done is I've basically going to summarize some of Dr. Castle's reflections as part of my talk. So I'll quickly go through. One question posed to NCIs: what do you see as the most important promising possibilities for and barriers to real progress in cancer prevention in the near future? And Dr. Castle wrote, there are several areas of promise. One area that we're working on very hard is precision cancer prevention. And what he means by that is you're going to evaluate on a person-by-person level the genetics of the person, the risk factors and lifestyle in order to tailor prevention strategies. So this is really a precision medicine approach, right? And at the same time, he wants to democratize cancer prevention, develop new strategies that might make proven prevention measures more broadly accessible, particularly for underserved populations. And he gives some examples here. So that is a component of prevention. The outreach must improve, and certainly any disadvantaged populations need to be focused on. As for barriers to progress, why is progress being relatively slow in this area? He sees 2 major issues called the prevention paradox, which I thought was interesting. If we're successful with prevention, sorry, my screen is freaking out here. If we're successful with prevention, there's nothing to observe because we've avoided a bad outcome. And this he'll call event bias. So people don't know what they avoided. So it's a little harder to document. Epidemiologists work at this. And a second barrier is benefits to harms ratio of any prevention-focused intervention. When we're talking about cancer prevention, we're primarily dealing generally with a healthy population. So tolerance of any side effects is very low. That's different than therapeutics. And so the bar is people will not tolerate anything that causes problems in a relatively healthy individual. So this is another great challenge. And in terms of intervention research, again, I'm going to give you some examples of prevention now, and then I'll get into early detection and early intervention. Again, I'm going to be going through the triad here. Prevention is a broad topic. Have you identified priorities? So what are NCI's priorities in terms of prevention? One is developing preventive agents, identifying druggable targets for preventive drugs, not therapeutic drugs. That work is anchored to molecular science, which is sort of my area of interest, understanding cancer-promoting signaling pathways in cancer cells. That's why your background needs to be robust in this respect in order to interrupt or interdict these events. We have to work on information development in order to tune our pharmacological agents or repurpose existing drugs for the use of cancer prevention. The second research arc is discovering biomarkers that can identify who is at the greatest risk of cancer. Obviously, if you're somebody who's obese, you're already elevating your risk of cancer. What are biomarkers we should be measuring? This is a non-trivial pursuit. And once we understand the biology and the genetics of cancer-related and treatment-related symptoms, that is called symptom science. And we can better tailor the use of current medications to prevent or alleviate symptoms and develop new or more effective medications in the future. And this is all considered important because it could impact survivorship. This is another major part of prevention. If you have cancer and you're successfully treated, what do you do with survivors of cancer? How do you prevent the cancer from recurring? This is, again, something the patients definitely want and the medical community is struggling to address. So keep that in mind as well. So cancer prevention by dietary constituents is generally considered a tale of failure and promise. So I'm going to give you a little bit of that story now. This is from a Lancet article a while back. And again, the theme here is heterogeneity in response. Why do people respond differently? This is, of course, very important for the therapeutics field as well. So I'm basically just borrowing from that field. Dietary bioactives are pleiotropic. And I would argue every drug that administered is also pleiotropic. But on the bioactive side, that pleiotropism is considered a huge liability. Nonetheless, the same liability exists for drugs as well. And we need to elucidate molecular mechanisms of action because, as NCI said, if we don't understand the biology, it's much harder to interdict whatever oncogenic processes are occurring. So this nice diagram shows basically what contributes to individual variability. It is, you have to separate responders from non-responders. That is the task. And what is the molecular byproduct of all of that? So I'll just use obesity as an example. If you say people are obese, you actually include in there, in this somewhat oversimplified context, normal BMI people who are metabolically healthy. Okay, hopefully that's like you and me. Obese BMI, but they're metabolically healthy. Normal BMI, metabolically unhealthy, and obese BMI, metabolically unhealthy. So we have at least 4 clinical categories for people who are obese. Are they all the same? All the biology would suggest they're very different, and they need to be handled differently. They must be binned differently. So that's a great challenge. And what also contributes to heterogeneity in response, I just pointed out the gut microbiome previously. So gut microbiota is associated with many chronic diseases in humans, and there is a tremendous amount of research now looking at microbes, gut microbes, and cancer, and I'll give you some examples today. Let's see, I'm doing okay on time so far. And let me just point out the very obvious, or maybe not so obvious, is the food that you eat has the most powerful impact on your microbiome. The number one effect is antibiotics and then diet. Okay, so what you eat affects your microbiome. Just keep that in mind. And host microbe interactions, there are well-documented effects, like in this nice science paper, on drug diet responsiveness and failures. So the gut microbiota has microbial nutrient metabolizing enzymes. So your diet and your biology itself can select for microbes that populate your gut, okay? And they can influence everything that comes into your body, including drugs. And therefore, there now is a growing field called precision nutrition, which is trying to personalize dietary recommendations for specific applications. It's in its infancy, but it's hobbling along. And this just shows you now there's a lot of sophistication entering into the cancer field on how the microbiome basically can influence drugs and either not. Some drugs can be basically modified, metabolized differently by the microbiome. And that's either a good or a bad thing, depending upon how you want the drug to persist or basically disappear. So keep that in mind. Microbiome drug interactions are now quite well documented. Here's one really interesting paper that just came out this year So I can't quite read the title because I probably need to move this somewhere. Yeah, let's put this over here. Now I can read it. Gut microbial metabolites facilitate anti-cancer therapy efficacy by modulating cytotoxic T cell immunity. Okay, so think of this story. The microbes are actually influencing the therapeutics ability to reverse T cell exhaustion. So if you don't think about the microbes, your drugs could fail in this respect. Oops, sorry, let me click back here. And this just shows you that gut microbial metabolites improve chemotherapy efficacy by regulating CD8 T cells. And in this case, a short chain fatty acid shown here, butyrate, is one of the mechanistic triggers that is influencing this ability of this T cell in order to target and kill the tumor cell. Okay, so that shows you just an example of a coming wave of papers where people now therapeutics cannot ignore the microbiome. They're interactive and influencing each other. And if you're interested in this biology, you better wake up and think about the microbiome, especially in the gut. Okay. What contributes to heterogeneity in response to treatment? Again, the theme I keep persisting in, cell heterogeneity. Of course, it turns out that not all cancers are alike. Like here, there are 4 classifications just for colon cancer itself. For example, if you have a CMS2 cancer, that's basically it's driven by an APC tumor suppressor deficiency, which is turning on Wnt signaling, et cetera, et cetera. And a specific therapeutic regimen might be targeted to this kind of genetic aberration as opposed to these other classes of tumor. And now the classifications are getting more and more complicated. But this is what clinicians are primarily using. And so there's a lot of interest in understanding tumor heterogeneity, how to treat it, and how to prevent it, and from developing anyway. And this just is a depiction of the modeling of human tumorigenesis, subclonal evolution of tumors. There's a lot of work in this particular area. And now there's a very sophisticated approach to look at the cells of origin of tumors. So in this paper published in 2018, they looked at over 10,000 tumors from 33 plus types of cancer, and they actually looked at the classification of these tumors, their molecular heterogeneity, and this is a huge effort to really create tumor atlases so that the cell composition and the molecular heterogeneity is now being defined for people to begin to target. And here's the immune landscape of tumors, so also published roughly at the same time, looking at how does the immune system change in response to very specific subtypes of cancers and what are the immune subtypes, therefore what kind of therapeutics. This is giving us a snapshot into individual precision medicine and perhaps chemoprevention approaches. This is just proof of principle. Here are just some of the comprehensive characterization of tumor suppressor genes and oncogenes, all within individual tumor types. And you can read so many of these papers. This is big data. This is systems biology, and I'll be getting back to it in just a second. So how do we unravel biology and address different shifting paradigms in cancer? That takes us to the field of single cell analysis, which all cancer therapeutics and prevention are now embarking on. And this field has exploded in the last 5 years. I'm going to give you some examples now. Basically, people are using a whole variety of single cell genomics and transcriptomics and other omics in order to begin to understand the complexity of the cancer they're trying to prevent or therapeutically attack. This just shows you a simple cartoon I actually used in a grant not too long ago, showing you single cell approaches to understand heterogeneity. And in this particular case, there is an effort to look at single cell metabolomics, which is still a discovery entity, not commercially available anywhere in the world, as far as I know. Single cell transcriptomics, which are being run quite frequently now. Single cell epigenomics, which is also commercially available, and a struggling but yet not really available single cell proteomics. That will only get to it when mass spec can accommodate it. But bottom line is, why are we doing all this? We want to do a multi-omic profiling, or deep phenotyping of tumors. Then we can really understand prevention and therapeutics and how to attack this. And this is happening now. Here is a paper, the earliest paper, one of the earliest papers I could find in Science in 2013, looking at single cell metabolomics. And like I said, this is just coming available at a discovery level. So it is not commercially available. And I believe only a few mass spec oriented gurus are doing this right now. We're actually trying this at Texas A&M right now. And I would say we're very much in our infancy here. Again, as I mentioned, there's a lot of work to construct landscapes or atlases on a single cell basis. So each kind of tumor can be characterized. You can see all the different cell types in there, and you can target your approaches to deal with it. Again, very complicated, very big data. You can use this big data approach on the single cell level to basically explore cell-cell interactions. So there's some amazing software that is becoming available to do that. This can allow you to explore autocrine, paracrine, juxtacrine, and endocrine interactions on a single cell basis, all within the tumors that you are trying to attack or prevent. So this is now becoming a reality. Here are some of the wonderful schemes that are occurring, taking place. Again, all for deep phenotyping. Deep phenotyping. Now, what I did is I superimposed my bias in here and said deep dietary phenotyping as an example. The diet is part of your exposome. You eat every day, you're consuming food. It is affecting your microbiome. A lot of molecular mechanisms are being altered. NCI still argues whether or not this is really an effective approach. The data are overwhelmingly clear. Diet is incredibly important. I'll show you a little data in a second. It can be used both for personalization and prevention capacities, again, in a single cell component, and prediction, et cetera, can come out of all of this. So I basically usurped this diagram from this interesting review article, and I'm superimposing a little bit of my nutritional bias in all of that. Other things that you can do to really look at prevention and therapeutics is using humanized mouse models as an example. So you take the tumor or cells from the tumor from a human and you put it into an immunodeficient animal, and basically you perform what's called a patient-derived orthotopic xenograft, and you can treat with drugs or chemoprevention agents to try to influence that cancer. So in other words, you're pre-screening the human by creating a mouse model of that human, and then you can then go into the human and resolve any matters. Again, some places are trying to do this. Another very important area I just want to introduce you is patient-derived organoids. This field was actually started in 2008 by Hans Clevers in the Netherlands. I was actually lucky to be in a sabbatical in his lab at the time. So I was the very first person to bring organoids to the United States of America. You probably wouldn't know that insignificant fact. But nonetheless, because of Dr. Clevers, organoids are basically state of the art now, and many people are using them. And how can you use them? Well, you can get these organoids developed from basically any tissue site now. So you go into the tumor, you collect some cells, you grow those cells up in a three-dimensional culture. You can use therapeutics to basically look at what happens to these cells. These cells basically are proxies for the human being you're studying. And again, you can add any other disease modeling to these things. And it's an extremely powerful platform. So people have created biobanks for all these organoids, and each patient, maybe at MD Anderson one day, there will be a biobank for that patient. And you can imagine the immense cost and how all this is dealt with, and I'll let you deal with that provocative thought process. What about interception research, early detection? Sorry, I got to speed up a little bit. This is back to NCI. A big part of prevention is early detection. So what are the NCI's thoughts on this? The big question is, can we detect the cancer at an early enough stage that we can reduce the risk of death from that cancer? So that's a good question. I just wanted to bring up as an example of that, liquid biopsy, which is a huge field that has now blossomed. People are taking blood, urine, sputum, and are looking for components in these liquid biopsies that basically can give you some idea of whether cancer is present or absent, as an example. And I'm not going to get into this field much, except to say that it is now emerged and it is helping to drive detection capabilities. What about early intervention? Well, again, the earlier intervene, the better in most cases, I think in all cases. So you must develop longitudinal deep phenotyping. You've got to be able to somehow sample the subject, the human being of interest, at multiple time points for first detection, intervention, return to wellness, and you'll build a molecular signature to do that. This involves different modeling techniques once you figure out how to do it. That's why the liquid biopsies are considered very appealing, because you're just collecting blood at different intervals. This can then be modeled in order to determine an individual's cells and their responsiveness of individual cells, and will help develop personalized treatment plans. So again, more systems biology with all kinds of longitudinal surveillance. And I'll just skip over that. So here's just a summary. Explore individual variability. How do you basically create an armamentarium to predict biological and behavioral response patterns, to basically personalize both therapeutics and chemoprevention? So I put this together from this nice review article from Zeisel. You must be able to evaluate the diet and look at dietary biomarkers, because I already mentioned diet is very important for cancer. And I think I had a slide if I didn't lose it. Genetic variation must be assessed. So you can look at basically all the genotype of an individual and predisposition to different cancers. You must examine epigenetic variation by assessment of epigenetic changes that could influence metabolism and chronic disease. You must look at microbiome variation, effect of diet and the microbiota populations and their functions. This is getting complicated, isn't it? Yes, it is. You must be able to look at exposure variation, methods to assess environmental exposures that obviously can dramatically impact cancer risk. You must look at lifestyle variation. What are the best biomarkers, instruments to assess lifestyle and behavior patterns? This was once considered a joke by NCI. It's now big time research, these lifestyle variation indicators. So there's lots of funding there now. Systems biology, a huge area across all of the life sciences and physical sciences, but this sits right in the middle of cancer research. We must utilize tools to assess interactions between omic data sets. We must be able to predict outcomes. So this is where the longitudinal data sets come into play across the spectrum of everything that I've listed. And we must translate into practice this information and develop policy. So if you're a policy person, this field is right for you as well. So there's tremendous amount of work here. Here's just one really cool systems biology example that I pulled out from a collaborator of ours, James Kai. You may know James, maybe not. He's at A&M. But basically, James developed a prediction tool. So how does it work? Well, it's really an ingenious, deep, computational program that allows you to predict the impact of one or more gene knockouts. So if you say, what does this gene do? Well, he can run a simulation that he's validated to knock out gene X, whatever that is, and show you what happens to all the signaling networks. So when you do your experiment, you have a targeted hypothesis to go after. He can also look at combinations of genes. So this is really a very interesting prediction tool, and just one example of those tools, one that I happen to know. So it's very important. So if you have, in our case, validation of that, we give him the data and he says whether or not his tool could predict for it. So I just thought that was really cool. It's called a virtual knockout tool. And back to NCI, we have a little time yet. NCI, basically, you can look at chemoprevention. A big area that is now receiving tremendous focus is immunoprevention, that I'm going to just talk about, because immunotherapy is obviously high on the list of NCI. Immunotherapy has been a great advance to cancer treatment, and we're targeting the immune system here and cancer surveillance by the immune system and the development of immunoprevention drugs. So basically just wanted to indicate that targeting the immune system is definitely incredibly important. Here's just an example of how the microbiome influences cancer immunotherapy. So again, if you're interested in targeting the immune response to cancer, you've got to think about the microbiome. I thought that was important. Other areas that also impact all this responsiveness and prevention is diet and exercise. NIH used to fund zero in this area. Now there is a lot of funding to look at diet and exercise. The thought is definitely out there that if you eat this specific thing or avoid this other thing, you'll prevent cancer. Unfortunately, no specific foods or activities are proven to prevent cancer. The reason why they say that is there's tremendous heterogeneity in response. But if once we get more sophisticated, we may be able to prescribe or individualize approaches so that specific foods and exercise may actually be prescribed, but we're not there yet. We know that obesity increases the risk here, it says, of 13 cancers. So clearly all this lifestyle is very important. And to live a long and healthy life, what do you got to do? So here's just an interesting article from Archives of Internal Medicine. Do 4 things for me today, and then my talk will have been successful, because you can reduce cancer risk by about 40% and chronic disease by 78%. What drug can do that? Almost nothing. You got to have a body mass index less than 30. You never smoke. You perform exercise at these intervals, and by golly, you eat a healthy diet, and we won't go into details there. Okay, back to diet again. I'm just going to finish up on this theme. So why are we wasting our time trying to do dietary chemoprevention? More than half of all cancer is diet related. Want me to say that again? More than half of all cancer is diet related. Okay, that includes obesity as part of that. So we should be focusing on this dimension as opposed to ignoring it. Here's just some papers that talk about nutrition, inflammation, and cancer triads. So just let you look at that. Nutrition, inflammation, and cancer again. This is a really nice paper, Nature Immunology. Overfeeding causes all these known effects below: metabolic syndrome, obesity, and basically supports a tumor supporting environment in your body. Okay, that's the reality. Enhances carcinogenesis, accelerates aging, and results in chemotherapy resistance. Okay, that's why all this is incredibly important. If you ignore this, therapeutics fail dismally. They won't make a dent in cancer. Okay, and you won't be able to afford anything. You got to deal with this stuff. And you need a lifelong adaptive process, something else that, of course, is a huge problem for any population to deal with. Nonetheless, this is the reality. Okay, if we want to keep people healthy longer and reduce the risk of cancer, we can't ignore these things. You can read lots of papers on this. For example, this was a nice paper, just show that people, you could intentionally cause weight loss and it would reduce the risk of several cancers. So they did studies, they monitored weight loss regimens, and they found significant decrease in risk markers for cancer. So you can make a dent in these things. Here's something really cool that's becoming even more important. So if you are a therapeutic nut and that's your call in life, are you going to ignore diet? The answer now is no. Published in Cancer Cell just a year ago, what does it say? Precision nutrition, which I've gently alluded to, and drug-based therapy are now converging. And it shows you that for all of these therapeutic drugs, there are now complementary dietary approaches that are being used in order to enhance the efficacy of these drugs. So, like it or not, therapeutics and diet and nutrition are coming together and will solidify. So you pick your diet here. If you're getting this kind of therapy, maybe you go on a cysteine restriction diet. And you say, well, I don't know anything about diet. I don't know anything about metabolism. Well, guess what? You're going to learn it if you're going to understand how your therapeutic either succeeds or fails. Okay, so just think about that as a provocative thing. And then I've left you with a few tables here on NCI to look at risk quantification, how you look at that on individuals, mechanistic foundation of all of this work. I'll let you read about that in the PDF that I sent you. Understanding basic biology. I can't encourage you more. You've got to understand the fundamental molecular mechanisms. Otherwise, your work is purely phenomenological and you will fail most of the time. Heterogeneity response, that's precision medicine. That's precision nutrition. It will become a reality. We just have to make it more cost effective. The timing of the intervention is very important. 5 minutes, I'm almost finished. effective prevention modalities, consideration of unintended effects. These are all very important to NCI. Obviously, therapeutics know all about these things. And then we come back to the reality of dealing with everything. So I dug out the 2019 budget from NCI. It's bigger now, but it's still billions of dollars, all right? Less than 1.5% of total biomedical research funding is devoted to prevention right now. Okay, maybe it bumped up to 1.6% recently. And here's some smart people writing in great journals about it, and we continue to ignore this. So you are not going to solve cancer by therapeutics, period. I love therapeutics, keep doing that, that's fantastic, but prevention is the only way to tip the tide of cancer, especially as we get more and more obese and more sedentary as a society. We've got to tell the granting agencies to fund more studies in this area, okay? And this is where it all happens. Prevention at NCI is at Shady Grove. They have a beautiful building. Check them out. Here's some recent grant announcements. And on that, I will conclude and take any questions. Thank you.
Rob, thank you very much. Indeed, as I said at the beginning, Rob is a true champion for prevention, cancer prevention, and cancer prevention research, and that really was a fine presentation. I genuinely appreciate it. Do you have any questions for Rob? And I see, Adam, you're starting off.
Yeah. So my question is, what sort of tools exist right now? Because I don't think you mentioned it, on sort of deconvoluting what parts of the microbiome, like which bacteria specifically play like sort of more key roles. I'm wondering if tools exist or if that's still just like something that is not well known. I'm curious what your thoughts are on that.
The field has really exploded in the last 10 years, and there's a very sophisticated understanding now. There are many unknowns, but in some cases specific genre of bacteria, classes of bacteria have been identified. Some do produce actual procarcinogenic byproducts, but the precise understanding of what's going on in humans is still an evolving process. But there are many computational tools. There are many, it's basically the conflation of the microbiology field and the cancer biology field and the systems biology field, et cetera, that have come together to definitely show us that different bacteria, and there's also fungi and viruses, all these things are definitely involved in determining risk and responsiveness to therapeutics. The precise
there are fungi in your microbiome.
Yeah, it's all down there. It's all interacting. Bacteria are the best understood of them, but basically there are clinical studies now looking at how therapeutics are being impacted by different microflora, et cetera. And when you have a dysbiosis, an abnormal microflora, how do you make it healthier? What are all the strategies, et cetera, et cetera? So it's really separate from my talk entirely, other than to what your appetite to show. If you are in prevention or therapeutics, you simply cannot ignore the microbiome, and you better start collaborating with somebody who has some appreciation for it, because that will probably improve the quality of your science.
I can interject there. There's also an interesting and emerging thing, because Rob is largely referring to the gut microbiome, but there's increasing interest in intratumoral microbiome. There are certain tumors that have a bacterial population within the tumor. Pancreatic cancer is one of those prototypes, and colorectal cancer as well. And There's a great deal of interest in the fact that the organisms within the tumor may be dictating their particularly immunoreactivity and responses. So yeah, it's a really remarkable area right now. Liesl, you have a question.
Thank you. Actually, first I wanted to say thank you for bringing organoids stateside, since I use colorectal PDOs every day. My question actually has kind of maybe an oversimplified question, and it has to do with chemoprevention for healthy obese populations, since it increases the risk of colorectal cancers by 30%. My question is, do you foresee a future where there will be like a chemoprevention in the form of like a vitamin that is would be administered to all obese populations, or do you think it just should be, I guess, the most at risk? I guess what it comes down to is kind of avoiding more personalized ones, since at the moment it's not available to everybody.
Well, the concept that would resonate best is what's called a prebiotic approach, where you would attempt to improve the condition of the microbiota of obese people, which is dysbiotic. It is considered abnormal, and the way to do that is to provide indigestible material substrate for the microbes to consume. When they consume things like dietary fiber, which is indigestible plant-derived carbohydrate, gets into your large intestine, is fermented, it will create a more hypoxic environment, because the microbes will basically utilize the byproducts of the fermentation process. Sort of getting into a long-winded response here. This causes basically the host, the host will utilize the byproducts of the microbial fermentation products and will create a more hypoxic gut, which is going to change the microbiome in a positive way. So you don't do it with giving people a vitamin. You do it by giving the substrate that allows the anaerobic microbes to thrive. This is the way we evolved, eating this kind of food. But Americans in general consume about 10 to 15 grams of fiber a day, and that's less than 50% of the recommendation. So as a result, you are not going to have an optimal microflora, because you're basically underwhelming them with substrate, and they cannot thrive. Different types of pathogens and other facultative anaerobes take over, and you have an unhealthy gut. You have an unhealthy gut microbe, bad things happen. This is what goes on in obesity. So I'm simplifying the intervention, but you will have to overcome the problem, if it's a microbiome problem, primarily at a substrate level. So you can't populate with microbes very readily, because they simply will not be retained in the gut. So you got to change the substrate flow, and that means diet.
There are some interesting studies on non-steroidal anti-inflammatories in some conditions, particularly in colorectal carcinogenesis. That indicates there may be a place for interventions that reduce inflammation within tissues as preventive agents as well. Kai, you have a question.
Oh, yes. Thank you, Robert, for a great talk. So I just have a question. Like for our Chinese peoples, we typically have a heavy diet. So do you have any suggestions for us?
You have a what kind of diet, sorry?
The related heavy diets for Chinese people, right? Than other countries.
Heavy diet?
Yes.
Heavy diet, yeah.
Can you give me a little more specifics? What do you mean by heavy diet?
Like, usually we will fry the vegetables before we eat it.
Oh, okay. So you take plant products, but you fry them in.
And yeah, we will put like more oils, maybe the diet will more salted.
Well, certainly how you prepare food can influence how it's processed by the body. But if you're frying in animal fat or versus vegetable, this will have a difference. The point of the matter is the fiber will not, if it's plant product and it's indigestible, it will still remain largely indigestible whether it's cooked or not, although processing can influence some of that. And what you want to do is increase the consumption of dietary fiber, indigestible carbohydrate, because that is the source of substrate that the microbes have developed on over hundreds of thousands of years of evolution for us. And when you don't eat that stuff, there's no replacement for it. And then you get a dysbiosis and less ideal things come about. So that's my simple response.
Thank you so much. And I think all of you should know that Rob and his team up at College Station in particular have a really fabulous program in microbiome research. There are some other ones within the medical center as well, working in that area. And if you see aspects of your work that might relate to dysbiosis and microbiome biology, they're great resources for that. We should bring this morning's sessions to a close. And Rob, thank you so much for a great closer in terms of the presentation. We have about almost an hour before we reconvene, and Dr. Ahn this afternoon is going to go into some depth in terms of both vaccines and antibody-based therapeutics. So it should be an interesting area, particularly knowing what we now know. So unless there are any other questions or comments, I'm going to bring this session to a close and see you all at 1 o'clock. Okay, guys?
Perfect. Okay. Let's see how to go back.
Arrows on the bottom, slide, which is slide 2 to 44. It's the arrows you have to know.
Okay, good. So we're going to discuss antibody drug discovery. And we have been discussing different drug modalities. So of course, we're focusing on small molecules for the last 3 days. This molecular weight has, yesterday say, ideally smaller than 400. That you have peptides. You have proteins. Yesterday we discussed, but they're long-lasting, usually lanterns. And of course, we have antibody. This actually is HPV vaccine Gardasil, which is not a drug molecule, but nevertheless is a virus-like particle, very large as a vaccine. And for the last few years, actually, we get FDA approval for the first time for gene therapy, first time for cell therapy. Yesterday, Dr. Cooney talked about T-cell therapies. And we also have approval for RNA-based therapeutics. This morning, yesterday, we also talked about RNA therapeutics. So for those of us working in drug discovery, actually, there's no better time. Actually, you have access to all these different modalities. So today, we're going to focus on monoclonal antibodies. So antibodies actually came with different structures themselves. So we talk about the IgG, and you have IgA, which is 2 IgG-like molecules linked by this common J chain. Here is the J chain here. And then you have IgD and IgE. And of course, you have this IgM, is a pentamer, 5 IgG-like molecules linked by this common J chain. So all these antibodies are natural immune molecules. They have very different functions. For example, IgA, IgM are part of the mucosal immunity. And you heard during the COVID pandemic, you heard a lot last year talk about testing for IgM versus IgG. And so IgM actually is the first line defense of the mucosal immunity against SARS-CoV-2. We can talk about that later. And among all the antibodies, IgD is the antibody actually, until this day, we do not know its function. We don't know what it does. And to me, it cannot be just a waste molecule. We just need to figure out exactly what the biological function is. And hopefully someday we can figure out. And of course, we discuss the antibody as a drug modality, but actually every day you have a laboratory, you experiments, you use antibody in cell biology. For example, antibody used in vaccine blotting, antibody use the immunoprecipitation, antibody use the flow cytometry, immunofluorescence microscopy, and of course another assay, which is use the antibody as a reagent. So just a little bit of history about antibodies. So we know that today, any given of us, we have at least 10 million naive unique B cells in our circulation. That means you have 10 million different unique antibodies, naive antibodies. So for a long time, people really did not know this antibody diversity came from, because you cannot have 10 million genes to encode the individual antibodies. It turned out that this antibody encoding genes, you have this light chain, you have a lambda light chain or kappa light chain. For lambda light chain is a variable region, you have up to 30 different exons. And for the constant region lambda, you have 1, 2, 3 different lambda constant region. For the kappa light chain, you also have up to 40 different variable exons, and you have also the J chain up to 5, and you have 1 common kappa chain. And for the heavy chain, you have the variable region up to 40 variable region, and you have 25 D chain, and you have 6 J chain, and a common constant region. So during the splashing of these genes, you can imagine the combination is really a huge number. So this discovery by Sushma Tonigova at MIT, basically he got a Nobel Prize for the discovery of his antibody diversity. This is important because we're going to talk about phase-displayed antibody libraries where we make this relevant to this antibody diversity here. And then let's take a look at antibody as a molecule. Here I use the IgG as a molecule. So antibody IgG molecule is a heterotetramer, has 2 unique, 2 identical heavy chains and 2 identical light chain. And the variable region heavy chain and the variable region light chain constitute the antigen binding pocket. So this is called if you link these 2, they call the single chain fragment, single chain FV. Remember this morning, Dr. Zhou talked about the CAR-T construct. This CAR-T construct, actually, we have this single chain FV fragment. Actually, that's this part of the molecule. The variable region from heavy chain, variable region from light chain, linked with a peptide linker. Actually, that can bind to the antigen of the target nutrient. And in addition to this, this Fab fragment, FAB fragment, the antibody also have the FC region. So the FC region actually is heavily glycosylated. The glycosylation is not random, actually mediate a lot of biological and immunological functions. For example, it's responsible in part for the long half-life of the antibodies. And this glycosylation also impacts the immune effector function, such as FC engagement of immune cells to mediate ADCC, that's antibody-dependent cellular cytotoxicity, which is the FC region can bind to the FC gamma receptors of NK cells that can mediate cancer cell killing, called ADCC. And the FC region can also engage the C1q immune cells, which mediate the complement, called the CMC, also CDC, which is another mechanism for how antibody clears cancer cells, also bacteria. And the FCT, as I said, can also interact with the gamma receptors, which mediate all kinds of immune effector functions, such as ADCC. The FC region of the antibody came from different isotypes, IgG1, IgG2, and IgG3, and IgG4. So at least here, actually, IgG1, 2, and 4 are commonly used in therapeutic antibody design. This morning, actually, there was a question from Mike Curran about asking, say, the CTLA4 antibody can inhibit the immune checkpoint function, can basically relieve the inhibitor function, but cannot clear the immune cell. Because the antibody was actually engineered as IgG4. IgG4 does not mediate most of the immune effector function like ADCC or ADCP, same. And last but not least, you have the FC region can engage the FcRn receptor, also known as the neonatal receptor, which is responsible for long half-life of the antibody. A human antibody, IgG antibody, has a half-life about 3 weeks in average. So that's a very long half-life. So here we talked a lot about the antibody trastuzumab, which is an antibody targeting the HER2 receptor. So HER2 is a tyrosine kinase receptor that mediates cell proliferation and metastasis. Therefore, the FC part of the molecule that bind to the HER2 receptor can inhibit the HER2 receptor mediated phosphorylation, can inhibit the cancer cell growth and migration and metastasis. And that's one mode of action for this antibody. In addition, the FC portion of the molecule, as IgG1, can engage NK cells, can kill cancer cells by this ADCC, called antibody-dependent cellular cytotoxicity. And this FC region of the antibody can also engage macrophage to mediate antibody-dependent cellular phagocytosis, which actually this mechanism was actually discovered in my laboratory to show that trastuzumab actually can kill cancer cells by not only ADCC, but also ADCP. In addition, this FC region of the molecule can bind to the FC gamma receptors cancer cells. Then the cancer cells can downregulate the HER2 receptor level of the cancer cells by inhibition of the messenger RNA transcription of the HER2 receptor. This work is also done in my lab, was published a few years ago. So just for one antibody, trastuzumab, you can tell that the antibody can kill cancer cell by at least 4 distinct modes of action. So inhibition of the signaling pathway, and engagement of NK cell to mediate ADCC, engagement of macrophage mediate antibody-dependent cellular phagocytosis, and also can downregulate the HER2 level by inhibiting the HER2 transcription of the HER2. So maybe there's more modes of action. So you compare with small molecule drugs, so antibody can offer multiple modes of action. This is one example. And if you start with antibody drug discovery programs, the first thing you want to do is the question asked is where the antibody came from. So antibodies can come from immunize the animals, we can immunize mouse, we can immunize rabbits, we can immunize other animals. For example, animals like camel, animals like llama, also shark, those animals, they produce antibodies without light chain. So these antibodies called nanobodies. So they are smaller, they only have a heavy chain. So nanobodies became a major source of antibody. We can talk about that later. If the antibodies came from the animals like a mouse or rabbit, you cannot use these antibodies as drug molecules, because if you give this antibody to a human, so we're going to generate called immune response, called immunogenicity, because it's a foreign protein. So we're going to clear these antibodies. So in order to make the animal antibodies as a drug molecules, we have to humanize these antibodies. So I will talk about this is a major antibody engineering process, how to humanize the animal antibody for drug discovery purposes. And there are people actually generate animals by, so mice, you can remove all the mice antibody encoding genes and replace with the human antibody encoding genes. And these transgenic animals, they produce human antibodies if you immunize with a human antigen. So those are called transgenic animals. Those actually are today is widely available to generate antibodies from animals. Actually, they produce human antibodies. And another source of antibody actually called a phage display. So we can, as I said, any of us have at least 7 million different unique B cells, unique antibody sequences. So we can get these antibody B cell sequences, display on the phage surface, and these large libraries up to 12 different antibodies can be used for screening of lead antibodies. Oops. And we can also generate antibodies directly from B cells. And this is called single B cell cloning of antibodies. This is particularly useful for infectious disease. In fact, some of the antibodies for COVID-19, like the Eli Lilly antibody, 2 antibodies in that cocktail, and one of the antibodies for Regeneron antibody actually also came from people infected with the COVID virus, and they generate antibody response. You can close the antibody, neutralize antibodies from these B cells, memory B cells. And you can also get antibodies from plasma B cells. And talking about antibodies from a mouse called Harbodomus. And so this is something you all heard about. So the Hybridoma, so B cells actually are they are terminal cells, so you cannot culture the B cells because they could die. So what Dr. Kohler at Milstein that time working at the medical research laboratory in Cambridge, UK. So they fused the memory B cell that express antibody with a cancer cell, myeloma cell, which is a immortal cell. So the hybrid cell called hybridoma, you can culture them basically forever. So that's for the first time we can actually. So this was reported in 1975. Really changed the antibody from a polyclonal to monoclonal antibody stage up to this day. So made a major big impact on the antibody drug discovery. And just a couple of words about the phage libraries. So what we do is we isolate B cells. So B cell antibodies actually are B cell receptors, right? So the antibodies are B cell receptors. So we isolate the B cells from donors, and then we clone the antibody heavy chain, light chain from these B cells. Then we link them as single chain FV fragments or as Fab fragments. Then display this bacterial phage, phenometric phage, M30 phage surface. So this phage actually can display, in this case, protein 3, up to 5 copies of the antibody is phenotypically linked with the protein 3. And then you can do a screening, and then you can get the antibody of interest by incubating with your antigen. So this is a diagram to show you how we isolate the antibody from individual plasma B cells. So this example was done in my lab. So basically, the monkeys are immunized with a dengue vaccine, and so 7 days after the boost, so we isolate plasma B cells, and through FACS sorting, we got the individual plasma B cells, and then clone the antibody encoding heavy chain light chain genes from individual B cells, and then convert it into IgG vector, then express it. So this is how we get it from plasma B cells. For memory B cells, so what we do is we isolate the memory B cells, and then incubate it with a human cytokine cocktail, including interleukin 21, and also feeder cells that are overexpressing CD40 ligand. So this cytokine and CD40 ligand actually can stimulate memory B cells to convert memory B cells into plasma B cells. So after 40 days of culture, these memory B cells, they convert into plasma B cells. They can secrete antibodies in the media. Then we can do some sort of a binding or functional assay to isolate, to select the positive values, and then convert this cloned antibody from these positive B cells, convert it to IgG, then we can do screening at a functional assay. And any questions so far? Okay, so let's continue. So when I talk about the antibody as drug modality, actually it covers not only monoclonal antibody, but some other variations. So the trastuzumab is a good example of a monoclonal antibody, which I talked to you before. And antibody actually can also conjugate with drugs, like chemo drugs, cytotoxics. So it's called in the form of antibody drug conjugates. This actually became a major drug modality. I will spend some time on this. And antibody drug conjugates is specifically for cancer indication, for tumor targeting. And there's also, you can conjugate antibody with antibiotics for bacterial infection. So this is called the AAC, so antibody antibiotic conjugates. And you can also conjugate antibody with radioactive. So this morning we talk about the radiation. So this antibody actually, radiation is sometimes broadly radiate the whole organ. With antibody, actually, we can more specifically target the radiation to the tumor side to minimize the side effect. And I told you earlier that the antibodies are very specific to its antigen. So what we can do is we can engineer antibodies with the bispecificity. So one antibody can target two different antigens, which I'm going to spend some time later on in the lecture. So yesterday, Dr. Rooney, also this morning, Dr. Zhou talked a lot about CAR-T, cell-based therapy. And if you think about it, the CAR-T therapy, the core technology is the antibody. So without the antibody, there's no CAR-T. So in my mind, CAR-T therapy is pretty much is an antibody modality, which I will also tell you more about this later. So, so I told you about antibodies. For monoantibody, we talk about it. We can use IgG1, IgG2, IgG4 as isotypes. IgG1, which engages the immune system, like ADCC, ADCP, and IgG4 does not. So for the current drugs like Keytruda, which target PD-1, also Opdivo target PD-1 from Merck, from BMS, they are all IgG4. So that time, because you already have antibodies targeting these immune checkpoints to activate the immune system. So that time, people actually do not want to overactive the immune system. So they made it into IgG4. The FC actually does not engage NK cells or macrophages, so try to minimize the potential side effect. And antibodies can also made into nanobodies. I told you antibodies from camel, from shark, from llama. They produce antibodies without light chain. They are smaller. They're called nanobodies. And antibody can be, as conjugated with drugs, ADC. And antibodies can also fuse with proteins like cytokine. So recently there's approval antibody fused with the interleukin-12, which is a very powerful cancer drug. This actually became a major area that the antibody protein fusion modalities. So I already talked about where the antibody came from animals, came from B cells, came from phage libraries, can be total synthetic. So I don't have time to talk about synthetic antibodies. And modes of action, mechanism of action, antibody can be agonist, antibody can be antagonists, antibodies can mediate the immune factor function. I told you about the HER2 antibody trastuzumab. Antibody can engage the T cell engaging. They can downregulate the receptor. They can inhibit receptor signaling. They can deplete the antigen. So all these can be individually or in combination can be the modes of action for antibodies. In the case of trastuzumab, actually, I already told you at least 4 different distinct modes of action for trastuzumab. And this actually is already obsolete, the 2019. So for protein-based antibody-based therapeutics, there are today actually there's over 100 approved antibody therapies. There are more in clinical trials. So the over 1,000 different antibodies approaches in clinical trials. For cell-based antibodies therapeutics, so here this is actually a review from Dr. Bill Zhou, who was used to be senior VP at Zhiqiang. And so in this review, and he classified the CAR T cells as antibody therapies. So this morning, Dr. Zhou actually said there's already 5 CAR T cell approved by the FDA. But of the 5 CAR T cells, 4 of them are targeting CD19. So in my mind, there's only actually 2 drugs, one CD19, one BCMA for prostate cancer. And there's also, in this case, also including ADC, all is a mix. There's a total about 1,200 these antibody-based modalities. This is 2019, 2 years ago. And Dr. Davis already showed this slide in his opening lecture that if you look at the top 10 selling drugs in 2018, 7 antibody. This is unsinkable. When you antibody as a drug modality only less than 25 years from today. So let me quickly walk through this. So the antibody called Humira, which is targeting TF-alpha for autoimmune diseases, including rheumatoid arthritis, Crohn's disease. And it's the best-selling drug that year, sold for about $20 billion per year for one drug. And the second one is Keytruda, which is targeted is a PD-1 immune checkpoint made by Merck. This year, Keytruda will be selling close to $12 billion. The third one is Herceptin, targeting the tyrosine kinase receptor. You can consider Herceptin as a targeted therapy, and Keytruda is immunotherapy. And Avastin is also a drug targeting YTF. Is actually blocks angiogenesis for multiple cancer types, including colon cancer. Rituximab is antibody targeting CD20, which depletes B cells, mostly used for B cell lymphoma. And Opdivo is antibody also targeting PD-1, which is marketed by BMS, which is competing with the Keytruda antibody. And antibody Sterella, which is antibody marketed by Zhiqiang, targeting the P40 subunit of interleukin 12 and interleukin 23 for psoriasis, Crohn's disease, and other autoimmune diseases. And if you look at 2020, the top 20 selling drugs, 14 are antibody-based. So this is mind-boggling to me. So you look at the biotechnology. We talk about companies in Boston, in San Francisco, San Diego, some of the hubs of biotech hubs. Most actually targeting antibody-based drugs that included CAR T cells. So that's why this became such a hard area for drug discovery, and including the efficacy, like this immune checkpoint antibody like Keytruda, which basically, Dr. Michael Curran said this morning, for skin cancer myeloma, 10 years ago, you have 11% chance of survival, and today is 80%. And so much so that in 2018, the Nobel Prize for Chemistry gave to three scientists. Actually, basically, two of them actually involved in the phage display. And Dr. George Smith, who is a professor at the University of Missouri in Columbia, Missouri, and he published a single-page science paper in 1985. He displayed a protein in the bacterial phage and shows the protein actually is functional. That led to Greg Waiter, who is working at MRC in England. And in 1989, he demonstrated that you can display a single-chain FUV fragment. That is a variable heavy chain, variable light chain of the antibody in a phage surface, and that phage can bind to the antigen of that antibody. And in the same year, the Nobel Prize for Medicine gave two scientists for Dr. Hodgel, who pioneered the PD-1 antibody. That's actually he was mostly involved in Opdivo, that's the BMS antibody. And overall, Dr. Jim Zalishin at Edison, who actually involved in the CDL4, which is also a BMS drug. So there was a controversy in the chemistry field saying that the chemistry Nobel Prize give actually to two biologists, not really chemists. But this just outlines, underscore the importance of antibody drug discovery, the impact on human health. And so my laboratory, in part funded by the separate drug discovery core. So we have the entire platform of antibody, molecular antibody drug discovery that also branch into antibody drug conjugation, biospecific antibodies, and CAR-T constructs. So what I'm going to do is in the next few minutes to walk you some of the examples of how we in academic lab go about antibody drug discovery. And so in our laboratory, we have antibodies. We can get antibodies from mice, from rabbits, from rat. You might ask why different animal species. So similar to small molecule discovery, we want to, if you have a validated target, you want to screen different libraries, like Cliff's drug discovery core in Texas A&M. So he has drugs from different sources. And yesterday, Dr. Demi Young's drug discovery core at Baylor, he has this called DAE code library. So, so in the industry, actually, what we do is you do know which library will give you the best leads. So the best idea, if you have resources, you screen multiple libraries, including actually natural products libraries, to make sure that you get the drug lead you need. So same thing here for antibodies. So we do not know if mice give us the best antibody or rabbit, so we do multiple sources. And we can get antibodies from plasma B cells of animals, of humans, and antibodies from memory B cells of human or animals. We can get antibodies from phage libraries. We can engineer antibodies with multi-specificity, including biospecific antibodies, antibody drug conjugates, engineer single-chain FUV fragment tailored for CAR-T cell construct. We also can express antibodies in pure cell lines for large-scale production for studies in non-human primate. And we also engineered antibodies across the blood barrier for neurodegenerative disease such as Alzheimer's disease. And we also generated synthetic nanobody libraries by physics display. And recently, actually, the Texas Therapeutics Institute recruited a new faculty member. Actually, we are very fortunate. Alex G from UC Riverside. His expertise actually is antibodies targeting complex membrane proteins, such as GPCRs, membrane-bound enzymes like MAPs, and I channels. These are difficult targets for antibodies traditionally. So we want to expand our antibody drug targets to include these complex membrane proteins. Okay, so let's walk through some of these drug modalities in detail. So let's talk about the antibody drug conjugates. So in this simple cartoon, you see the antibody here, right? Let's say this is a trastuzumab. And the trastuzumab antibody actually bind to the receptor HER2, which is a tyrosine kinase receptor. On this trastuzumab, you can actually link a chemo drug. And once the antibody binds to the receptor, then this complex will induce the receptor-mediated endocytosis. So the entire complex is internalized. Once internalized, specific proteases is larger due to release the drug molecule inside the cell, then kill the cancer cell. So before the antibody drug conjugate internalized, this drug molecule is stable. It's not released in circulation. So that's why it can reduce the side effect of chemotherapy. And its concept is very simple. Actually, you practice is very difficult. The question is, where you go to conjugate the drug? Is it here or it's here? The next question is how many drug molecules you want to conjugate to the antibody? And what drugs you going to conjugate? So these are very complex chemistry, biology questions. So in this field, we need more potent payloads, and we need more better linkers to link the payload with the antibody. So linker chemistry. And we talked about this yesterday. Antibodies and vaccines are biologics. They are very difficult to make. Can you imagine antibody with the drug molecules, the antibody drug conjugates is even more complex. So we need to improve the manufacturing process. And these are actually all academic questions. And let's walk you through this bispecific antibody. So in this simple case, you can actually engineer the antibody with two arms. One arm bound to one antibody, another arm bound to another antibody. A simple example would be one arm antibody bound to CD3, another arm antibody bound to APCAM. So this bispecific antibody already approved by FDA for malignant ascites. And another bispecific antibody is called BITE, a bispecific T-cell engaging construct. So basically, you see it's actually a very small fragment, two single chain F way linked together. in this example is actually CD3, CD19 is also approved for acute lymphoid leukemia. I think I have a diagram. Okay, maybe not. So you can imagine there are different variations of this construct. You can make a new antibody full IgG with single chain at the same terminus of the heavy chain at different sizes. So this is actually a very active field of investigation, both in academia and in industry, and mostly actually is the biotech sector. So so this is actually a summary slide summarize so-called immunotherapy modalities, which I already talked quite a bit already. So let's just review this. So let's say you have a malignant cell, cancer cell, and you have a PD-1 antibody, immune checkpoint inhibitor is a monoclonal antibody. They can bind to PD-1 and then activate T cell to kill cancer cell. And this is monoclonal antibody. The bispecific antibody actually is called BITE. You can engage bind to CD3 T cell, and the other arm bind to CD19 as a cancer cell. So this bispecific antibody brings T cell proximity to the cancer cell, that T cell can kill the cancer cell. And you can also engineer CAR T cells, which is the CAR, this is actually the antibody that target CD19 can achieve the same thing. And we already talked about the antibody targeting CD20 rituximab can deplete B cell for B cell lymphoma. So this is basically summarize the different modalities. Again, in this Nature review, consider that CAR T cell actually as an antibody immunotherapy modality because the key actually is the antibody. Okay, I do have a slide to show you this BITE concept. So you take a CD3 targeting monoclonal antibody, and you take the variable chain, heavy chain, light chain, you make it to a single chain fragment. Then you link the single chain fragment from a CD19 antibody. So this construct called the BITE, called the bispecific T cell engaging. So this molecule, the CD3 part of the antibody bind to the CD3 T cell. T cell, CD3 is a marker for cytotoxic T cell. Not only this antibody bind to the T cell, but also activate the T cell. So the other arm of the antibody bind to CD19 positive tumor cell. And by doing so, brings a toxic T cell proximity to the cancer cell, then the T cell can kill the cancer cell. So this drug already approved is a drug actually marketed by Imaging and used for B cell non-Hodgkin's lymphoma and B precursor acute lymphocytic leukemia, ALL. And this is actually a bispecific antibody made in my lab targeting virus. So, so the virus actually including COVID-19 virus. So when the virus infect the cell, and some of the viral protein actually is actually decorated the infected cell. In this case, the HCM with human cytomegalovirus infect a normal cell, and infect the virus infect the cell. So the valve of the viral protein is called glycoprotein B, is actually on the surface of the infected cell. So what we did is that we have a bispecific antibody recognize this viral protein, glycoprotein B, and another arm of antibody targeting CD3. So by doing so, the bispecific antibody brings the T cell proximity to the viral infected cell. Then it can kill the cancer cell. So this is exact same concept as the bispecific T cell engaged antibody kill cancer cell. The same concept. So this afternoon we talk about the vaccine. So like say the COVID vaccine, we want to induce both T cell immunity and antibody immunity. So this is the T cell immunity. So once you have T cell immunity, T cell actually can kill infected cells, but antibody cannot. Antibody can only remove circulating viruses. Okay, I want to touch base briefly on humanization. And once you get a mouse antibody targeting the antigen, so we need to humanize it. So let's say this is the antibody for mouse. So the mouse antibody development region has CDR1, CDR2, CDR3. These are called the hypervariable region of the antibody. Actually, they bind to the antigen. So these red color, they call the frame region. They are frame 1, 2, 3, and 4. So we can find a human antibody, which is the frame is called the region called the blue. So frame 1, 2, 3, and 4. So by engineering, we can transfer the CDR regions of the mouse antibody or animal antibody to the frame region of a human antibody. So this antibody is called a humanized antibody because the CDR regions are immune privileged. So we usually do not generate antibodies targeting the CDRs. Of course, this is an oversimplification of the process because just simply grafting the CDR to the frame of a human will not work. You will kill the antibody activity. But you need to do a lot of this so-called back mutations to get the activity of the antibody back. So I do want to have time to go through the entire process. So you can imagine this is a part of the optimization stage, similar to a medicinal chemistry process. Another thing is called affinity maturation. So for antibody, you talk about how tight the antibody bind to the antigen. So it's called affinity. This also applies for small molecule bind to the protein. We also talk about KD affinity. So here's an example which I did in my lab actually quite a few years ago. So we generated the antibody targeting the interleukin-13 receptor alpha-1 subunit is for asthma treatment. This antibody right now actually phase 3 clinical trials. So we generated antibody called type G5. This antibody, I show you here the heavy chain CDR3 and large chain CDR3. These two CDRs are the most important, contribute to majority of the antigen binding. So this antibody gives us KD of 861 picomolar. Is a good antibody. But then we use the fixed display, we randomly mutated the CDR region, the first round mutation, we mutated one amino acid from phenylalanine to methionine, from F to M. We gain the affinity by almost 10-fold. So this antibody actually is 99 picomolar, about tenfold better than the original antibody. Then further mutations, you use additional mutations in both heavy chain and light chain. You read these mutations. And through several routes of mutagenesis, we were able to get the antibody down to 20 picomolar. And this is almost equivalent to a medicinal chemistry program where you can make the antibody, you can use small molecule more potent and also more selective. But for antibodies, the affinity maturation is mostly to increase potency, not selectivity, because antibody by definition are very selective, are very specific to the antigen. And here I show you one example of the general antibodies from rabbit. So in this case, okay, so we immunize the rabbit with the antigen called LLB4. It's actually a new immune checkpoint inhibitor receptor. And then we, after several boosts, we isolate the individual memory B cells. And from these individual memory B cells, we culture these individual cells. Then they create antibodies. We do screening. Then the positive screens, we actually get the antibodies. And so here I show you, we do 5 immunization steps. This is a 6-month long protocol. So we try to reduce the most potent antibody in the rabbit. In this case, we use rabbit because the rabbit give us enough serum, we can isolate enough PBMC to do the single cell culture. So we culture the B cell, we do a body assay, we include antibody from the rabbit B cells, then we also lead, we do the humanization because antibody from a rabbit. Then we do the select the clinical candidate. Here is a summary of this project. So basically, we identified 229 positive B cells. I just going to show you the numbers we go through. And we were able to, using reporter assay, liquid blocking assay, FC cross-linking assay, we were able to narrow down to 229 to 65 antibodies. From the 65, we were able to express 34 antibodies. From these 34, we did a battery of assays, reporter assay, liquid blocking assay, FC cross-link assay, epitope binding, affinity measurement, in vivo studies, humanization. We narrowed down to 2 antibodies. So this is just to give you an example, roughly how we do antibody discovery. So this particular antibody actually was reported at least the Nature paper in 2018 and a cancer immunology research paper in 2019. This antibody actually right now is already in clinical phase 1 clinical trial for acute myeloid leukemia, which I'm going to talk about this specific program next Thursday. Where I discuss some of the success stories of this program. And again, so this is a very quickly touch base. I mentioned the CAR-T. So our libraries are single chain if we display the phage libraries. So after we identify antibodies from the library, in this case also targeted this LRB4 CAR-T for leukemia. So actually we made a CAR-T, and I do want to go through this whole, yesterday Dr. Looney talked about this, also Dr. Zhou this morning talked about the first, second, third, fourth generation of CAR-T constructs. So this is actually the second generation, which is widely used. It uses 4-1BB co-stimulatory signal. And just make a long story short, so the CAR-T actually works for this particular leukemia, acute model leukemia model. Was published in Molecular Therapy from our group a couple of years ago. And now I'm going to touch base a little bit about ADC, antibody conjugates. And so the Texas Therapeutic Institute, so we were fortunate to recruit a very talented chemist by the name of Kyoji Tatsugama. So he, a script trade chemist, was able to devise some of the most advanced linker chemistry to use the industry today. And so I just show you, so we published some papers here. So he was able to have this called a branch linker chemistry. You can link conjugate 4 drugs per antibody. You can link 8 drugs or 16 drugs. He can also link different drugs on the same antibody molecule called dual mode of action. And this is actually, there's just a couple months ago, we have a publication in Nature Communications show that this dual drug payload antibody can kill heterogeneous breast cancer, triple negative breast cancer. And so I don't have time. This is not to describe this, but so we do have this very novel antibody drug conjugate platform. And very quickly, I want to show you. So the antibody I got showed you earlier came from immunized mice, right? So now I'm going to show you antibody actually got from the phage library of a lab. So we have a program targeting the SARS-CoV-2 virus. So we paired our library, and so we got 149 phage antibodies that bind to the receptor body domain of the virus. From 149, we will narrow down to 35 antibodies. From 35, we will further narrow down to 30. Then we did all kinds of studies. We narrowed down to 1 antibody. Actually, in this case, we convert this antibody to RGM. Because I showed you the RGM antibody is a part of the secreted mucosal immunity, first-line defense for viral infection. So this particular antibody actually delivered intranasally, and intranasally, and so this antibody was published this year in both Nature Communications and in Nature, outline this very success story. And this IgM antibody works for all the mutates, and including Delta variant. It's in clinical trials. So if it works, so everybody can carry a nebulator in your pocket. You just spray it, lasts for weeks, and almost like a chemical mask. I'm going to actually talk about this a bit more next Thursday to show how this antibody was discovered, how it works. And we also make bispecific antibodies, for COVID. This is a paper actually under revision in Nature Medicine. I don't want to have time to go through this. So lastly, I want to touch base the antibodies actually cross the blood barrier for neurodegenerative diseases. And so a simple concept. So this is a blood barrier, okay? So this is the blood vessel, and this is the brain. And so we want to have the antibody cross the barrier, get inside the brain to engage the neural target. And one of the BBB receptor called a transferrin receptor. So transferrin is a receptor actually shuffles RNA molecules from blood to the brain. So both the ferric and the ferrous RNA molecules mediate the redox reactions. And the redox reactions are very important for the brain. And so this is one of the most efficient protein that can traffic molecules from blood to the brain. So what we did, what people did here is actually to construct a bispecific antibody. One antibody bound to the transferrin receptor. So the transferrin receptor can flip this antibody from the circulation inside the brain. Once inside the brain, the other arm antibody, for example, can target the A-beta peptide, then can clear. So this is the whole. So we have this technology, and this is for neurodegenerative disease, but also for GBM, other brain tumor. So we will deliver antibodies for cancer therapy. So this is very relevant for. Okay, so Peter and Shruti, what I'm going to do next is spend about a couple minutes to discuss the reproducibility crisis you just discovered, because I do think we have I have time opportunity to do this. So this is important because your paper in 2017 in Nature. Reported between 10 to 15% of scientific research published can be reproduced. If it's 10%, that means 90% of what we do cannot be reproduced. If it's 50%, that's half. And so $28 billion of the US law, the money spent for clinical development of drugs is wasted because the target is not, based on published work, that's not fully validated. And this report further showed that the four major reasons for this reproducibility, 36% came from biological reagents and reference materials wrong. And this is a very important, so I came from industry before I came back to academia. So how many of you have received email messages from your colleagues saying, I'm working on colon cancer. I need a particular cell line. Who in our department has this cell line? Can I get a vial? I think this happened to a lot of you. And the problem that is those cell lines you get from your lab mates or from your neighbor's lab, very likely those cell lines are contaminated. They're not really the cell line that you try to believe in. And there's several studies. There's a very good study in the Salk Institute in San Diego. There's 3 labs working on a particular cancer type, and they got their cell lines and try to authenticate the cell line. Sure enough, 90% of the people, the cell lines are not was intended. So this is a big problem. So today, if you publish a paper, some of the journals, like AACR journals in Nature, these big journals, they ask you, say, you have to guarantee that the cell line you use in your study are real. And you HI like AHR funding, you have to authenticate to sign off, say that you could use the cell line or the biological material. That's real. And 27% of the data cannot be reproduced because of study design. And so we talk about statistics. We talk about so yesterday I was talking about make good notes and maintain good protocols. Spend time to do your study design before you initiate your experiments. And 25% came from after you get the data, actually you did not analyze correctly. And 10% came from laboratory protocols. So what's missing here is say that people are intentionally to fabricate data. So that's actually very minor, very small percentage. It's not even counted here. So we publish papers people cannot repeat. It's not because we make up data. It's very much not intentional. It's all here. At 2011, the Wall Street Journal has a 2-page Sunday report to show that Bayer, which is a pharmaceutical company, who over the years tried to validate 67 drug targets in academic journals. I can tell you those 90% of papers are probably these big journals like Nature, Cell, or Science. And 64% of these drug targets cannot be validated. It's close to 2/3. That's what the number I showed. This is actually published in the Nature Review Drug Discovery. And this publication actually has a major impact in the US Congress that year. That year actually was one of the driving force for the creation of the NCAD, the National Center for Translational Research, basically to help NIH to really focus on translation and drug discovery. And
Zhiqiang, as the official timekeeper,
okay.
I want to let you know we're at 4 o'clock.
Okay. Okay, last slide. So in 2017, there's another Wall Street Journal Sunday review. Again, 2 pages. So the title of this review is the dismal size in search of cure. This is directly relevant to drug discovery. And this in this particular report, I give you 2 examples. One example was the ICLAC, the International Cell Line Authentication Committee, showed that there are 450 mislabeled cashless cell lines. 130 of those actually are HeLa cells. And there are over 100 solid publications using these HeLa cells pretend to be cashless cells. Those completely cannot be repeated. And another example, which is in 1976, Emily Edison released a cell line called MDA-MB425. It said it's a breast cancer cell line. And 15 years later, it actually turned to be is a melanoma cell line. And that's already have hundreds of papers published. So in the year 2000, there was an announcement saying we cannot use this cell line as a breast cancer cell line. So we need to stop this research. It's all raw. And even after that, they still published at least 900 papers. So I will stop here and to walk you through this. I thought this reproducibility is important, particularly for drug discovery. I just cannot emphasize enough how important we as scientists first learn how to do science. Okay, I'm open for questions or discussion.
Can I just make a comment here, Zhiqiang? Thank you very much indeed for really that wonderful review in terms of doing that. And I think there are a couple of aspects to it. First of all, I think that one of the things of you guys at various stages in your training, the interesting feature is you will have your own laboratories very soon. And these issues become of major concern, not because of your own personal research, but because of the research programs that you end up supervising with your own next generation of trainees and the issues and concerns. And so very often, you know, it's just a flip of a coin before you guys are running your own programs, and issues of rigor and reproducibility are going to be concerns for you. The other thing is just to know that an integral part of our training program is the Gulf Coast Consortium's Rigor and Reproducibility Workshop, where all of you will be asked to spend a day as a part of that workshop, addressing many of these issues and understanding exactly what tools are available now to do that. You know, what Zhiqiang is pointing out is an era where folks were very casual about this. As he pointed out, there's a lot more checks and balances in terms of that, and core laboratories that we have within the medical center, particularly in MD Anderson, for the validation and certification of cell lines that are available to you to help make sure that what you're working with is in fact placed. So there are a lot of resources that are going to be available, that are available to you and will be important. But yeah, it's kind of a stunning revelation to know that. I always kind of look back on my own scientific career and I wonder just what the heck the cells we were working with really were, but that's the way it goes. Let's open it up for discussion with Zhiqiang and questions you might have about engineering antibodies. My only other comment is, as Zhiqiang pointed out, his laboratory is a secret core. It's part of our network. And so this is a resource that's available to all of you, both to work with the core and also to potentially do brief rotations in the core to get a hands-on feel for some of these technologies. So let me open it up for discussion. A question over there, Harman?
Yes, thank you for the great talk. I'm curious about the frequency of ADA, the anti-drug antibodies in immunocompetent animal models. Is this a problem that that's often observed with engineered antibodies and antibody-drug conjugates? And how could we recognize this problem in our models? Thanks.
Yeah, so that's a good question. So what Harman asking is called ADA, so antibody drug anti-drug antibody, right? So basically, like you have I said, if you have an animal antibody, you cannot give the human because they could have a anti-antibody, anti-drug antibody response, right? So that's why we need to humanize it, and so oftentimes we engineer antibodies. So how big this antibody drug response would be. So there's another term of this called immunogenicity. Of course, for vaccine, we want to have immunogenicity. That's where we get all this antibody response. But for antibody drug, we do not want that. So I can give you one example, actually, is very compelling to me. Was the year 2004, there are two antibodies approved for clinical use. One antibody is called Xolair, actually the antibody targeting the IgE antibody for asthma and allergic reaction. That antibody came from the fully human phage display antibody, the human antibody, fully human antibody. Sorry, Humira. Humira is a fully human antibody targeting TNF-alpha for autoimmune diseases. And Xolair targeting IgE is a humanized antibody from a mouse. So naturally, you would think that a fully human antibody would have less immunogenicity, right? Versus actually the opposite is true. So in the clinical setting, actually doctors found that there's way more antibody drug response to Humira than to the humanized antibody. Turns out that the Humira antibody has a very high affinity to the TNF-alpha, the protein, and the immune complex, the TNF-alpha antibody complex, it became immunogenic. So our immune system knows this. If antibody bind to something, that's actually is a target for removal. So the immunogenicity is not came from the drug itself. It actually came from the drug antibody complex. So that's something that you cannot control because it's related to the target. And so because Humira is such an important antibody, so actually for some patients, they actually have to use the immune suppression in order to use Humira. And you do immune suppression using Humira, you also have infection. You have to use antibiotics. So in order to use Humira, you need 2 more drugs. So to answer your question, so immunogenicity today is not a big issue. So we can resolve it. If it's a target-related, disease-related, so we can engineer. There's also computer programs to map T cell, B cell epitopes. If there's a B cell, T cell epitopes, you can engineer them away. But
if I understood Harman's question right, is there a possibility of haptenizing when the drug gets conjugated to the antibody and with the linkers? Is there a haptenization such that you may get antibodies directed against the ADC essentially as a newly haptenized entity?
So Harman, are you talking about ADC or just about antibody?
Just about. I thought Harman was asking about ADC actually.
Oh, I asked about both because I knew that the engineered antibodies were more in your experience. My particular interest would be the ADCs.
Harman is talk about the antibody drug, anti-drug antibody ADA. That's you give antibody to a human. So the drug is the antibody. It's called antibody. For antibody drug conjugates, they are. So Peter, I do think we have enough data to show that once you, most times antibody drug conjugates is most likely you have the monoclonal antibody approved that drug first, like trastuzumab, Herceptin. Then you conjugate it, then you approve the ADC. So the antibody itself already goes through the immunogenicity sort of. So the question is, after you got to conjugate the drug, can you create a new epitope called a neoepitope? And I thought I knew the literature about your antibody, but you got me this time. I had not say a paper to talk about immunogenicity against ADC yet.
But that's, as you point out, it's apparently practically not a problem in terms of doing it. You'd be reading about it in the literature.
Yes, I'm looking for it.
Ryan, you had a question?
Yeah, I have a question. I'm just curious about, you're talking about the ADC and that you could conjugate the drug at different position. And I was just wondering how you control the position where you want to conjugate your drug. Just a naive question, maybe, I don't know.
Yeah, no, that's a very good question. So you can randomly conjugate the drug as the large residues because antibody has multiple larges. Those are not very good. So today is all site-specific conjugation, and so you can design, you can introduce a specific amino acid.
Okay.
Use antibody location, and you design linker chemistry that specifically conjugate at the
specific position.
Yeah, specific site. You can also there's this term called antibody drug ratio (ADR). So you want to say sometimes you want to conjugate one antibody, two drug molecules per antibody, right? Because they have a antibody has two heavy chain, two light chain, and so sometimes your drug actually has the one antibody average 1.5 drugs. So there's heterogeneity. So that's actually a pretty big issue for manufacturing. So the linker chemistry, the biggest task is to the linker is stable and you want to have the ADR close to say 1 to 2, 1 to 4, depending on how many drugs you want to conjugate.
Okay, thank you.
Do we have any other questions? Well, I really appreciate. Chad, you've got. I'm sorry, I didn't see your hand up, Chad. Great, go ahead, Chad. Yes.
So first of all, thank you for a fascinating talk. And I was curious because most of the drugs and you have showed are targeting cell surface receptors or proteins. Is it feasible to have it target cytoplasmic proteins? And specifically you mentioned yesterday the PROTEC technology. Is that something that could happen within the cytoplasm and send a specific protein for degradation?
Yeah. So that's a good question. So most of the antibodies today, I would say all the antibodies today, targeting either a receptor, a membrane-bound protein, or a circulating protein, like a TF-alpha. That's a circulating protein. Also, like IGF, which is a angiogenesis factor. That's a protein. So far we cannot target the proteins, intracellular proteins, like kinase inside the cell. So I alluded earlier that antibody actually cannot even readily cross the brain-blood barrier. So this some of the neurodegenerative targets and also brain tumor like GBM. Actually, Kyoji got R35 from NIH, just focusing on how to deliver antibodies across the BBB. And this a major effort in our group here. And so there are academic labs, also industry actually try to deliver antibodies inside the cell. And there's two approaches. One is actually through a viral vector, which expresses an antibody fragment. And that delivery inside the cell, the antibody expressed but not secreted. So the antibody stays inside the cell. So this is still very early stages, not ready for drug discovery purposes yet. And another way is actually, I showed you the BBB, the transferrin receptor, the concept. There's also cells actually has receptors can internalize by specific antibody. You can flip in. So those actually are all in the research stage and not ready for drug discovery purposes. And also, Che, you asked me a question about the PROTEC, right? Yesterday, when Dr. Liu talked about PROTAC, I asked him a question about this particular publication early this year from Jimmy Welch's lab in UCSF. So that actually the antibody is not cannot get used at the cell. It's targeting some E3 ligase actually has an extracellular domain, as you know. So this antibody still stay outside the cell, but engages the E3 ligase. And through a bispecific construct can engage the targeted protein. That example is PDL1, which is also a membrane protein. And so it's that PROTAC is cannot get used at the cell. It's actually still an antibody outside the cell.
Is there a way to deliver it like how Fugene works, like a liposome?
Yeah, you asked me a question about so tell me, can you tell us about your idea of your PROTAC idea, or is this a secret?
Off record, I will tell you.
Okay, you call me. You call me. Okay.
Chen, let me add a little bit, to Quan's answer to you. So actually, there's another technique which is called LITAC. So LITAC is a little bit different from the antibody-based PROTAC. So actually, that is based on a glycoprotein, membrane protein. So which membrane protein recognize glycosylated antibody. So then the antibody basically bind to your target, membrane target. The other side actually bind to that sugar receptor. Whenever the sugar receptor bind to the glycosylated antibody, it will internalize the whole thing, including your targeted protein, to the lysosome. And in the lysosome, the membrane protein is degraded. This was developed by the Caroline Bottozzi in UC Berkeley. Actually, she just started a company working on the technique to develop different kind of therapeutics. Okay, so you can check on that, which is called LITAC, LYTAC. So that may be I would consider that probably simpler than the basically bi antibody, di antibody based PROTAC, because for those you have to conjugate two antibody together. It's a pretty big, and you create some kind of spatial issue for the E3 ligase to recognize your membrane protein. And also PROTAC, you have to rely on E3 activity. But for LITAC, so it doesn't rely on E3 ligase activity as long as the thing is internalized to the lysosome, is degraded. Okay, you can check on that.
Thank you very much. Yeah, it seems like I'll have to catch up with both of you. I'm actually writing a grant. I would like to add it to my grant. So.
I think for PROTAC, I think Dr. Liu is a true expert. I'm not.
we also work on the different way to do the for membrane proteins. That is to develop the cyclic peptide. This is much smaller than antibody. We have a bifunctional cyclic peptide. One side bind to membrane, your targeted membrane protein. The other side, which is really targeting the E3 enzyme. So in that way, so we can also do the same thing, which basically bring your target and the E3 ligase together for ongoing ubiquitination. There are different ways to do it.
Right. I'm going to use my executive authority at this point to bring the session to a close. It's been a phenomenal day. One of the things I'm noticing with Zoom and the gallery view and everything, you can see a portrait of fatigue as I look across the faces here in terms of doing it. I really appreciate you all hanging in there. I think we've heard some wonderful science, some wonderful ideas today. And hopefully we can all go and relax a little bit after doing that. I would like to thank Zhiqiang for taking the afternoon basically to share with you his insights and his expertise.
And so I have to prepare for tomorrow's 3 lectures. So tomorrow we're going to actually, really to me, is the hardcore of drug discovery. That's I remember is the value of death. From academic discovery to clinical development is this preclinical stage. this is called the value of death,
Yeah.
which I will do. So this is a formulation, drug metabolism, pharmacokinetics, and tox studies. This actually relate to lead optimization, lead discovery. So if we do not do good job of lead optimization, lead discovery, most of the drugs will actually fail in this. You cannot formulate it. You cannot. They do not have good half-life, and they are toxic. And so that's why I said earlier that we are not really doing drug discovery. We are discover a probe. And yesterday you heard from Scott Capuchin say that when you look at the drug, you can manipulate. So tomorrow to me is most relevant to this course is formulation, drug metabolism, pharmacokinetics, and so tomorrow will be a big morning.
And the afternoon.
And afternoon, yeah.
Where we talk about core labs that are available to help you support your pharmacokinetics and tox studies and other
Yes,
things.
yeah. Tomorrow, of course, afternoon. I'm talking about me for me. Get ready for tomorrow morning. I'm going to enjoy this afternoon. Okay, great. What else?
We'll move on to development tomorrow, and a lot more to talk about. But we'll see everybody at 8:30 if you can make it. It's really helpful to chat and hear what's people's thoughts are and what things we need to be paying attention to.
And tomorrow morning, 8 o'clock, where we are fresh, we can also discuss any question you have for today. So we can.
8:30.
8:30, 8 o'clock.
8:30, not 8.
None of us are fresh.
8:30, okay. Yeah.
All right, guys. Listen,
Yeah.
take care. Thanks, everybody, very much.
Okay,
It's been
bye.
a heck of a day. We'll see you tomorrow.
Goodbye.
Thank you.